Thank you very much. So first of all, let me start by thanking the organizers, so Hamanaka-san, for the kind invitation. It's a great honor to be in Japan again. So the title of my talk, as you just heard, is Lacks Integrability. So I want to give 3 talks which are progressively less and less introductory. So integrability and the relationship to what's called holomorphic-topological gauge theories. So let me start by giving an overview to set the context and to tell you what the outline of these 3 lectures are. So first of all, overview. So the talks are based on this general principle, which was first pointed out or discovered by Costello and then Yamazaki, Witten, and Costello. So the general principle is that there is some relationship, some deep relationship between, on the one hand, the notion of lax integrability. So we have lax integrable models, or more generally, these will be lax integrable field theories. So integrable field theories, which I'll abbreviate as IFTs. And these are on some d-dimensional manifold. So to begin with, it will be 1-dimensional. And throughout the lectures, I'll increase the dimension. D-dimensional manifold M. So on the one side of this correspondence, we have these integrable field theories, and more precisely, the emphasis is on lax integrable. So I'll explain precisely what this means if you're not familiar with this concept. And on the other hand, we have this notion of holomorphic/topological gauge theories. So these are abbreviated as HT usually. So gauge theories. And these live on a two extra dimensional manifold. So they live on D+2 manifold, D+2 dimensional. The idea being that these extra 2 dimensions, 2 real extra dimensions, are 1 complex extra dimension. So we're looking at a theory on the same manifold as we started with, but crossed with a Riemann surface. So this is where the underlying spectral parameter of the lax matrix or the lax connection is living. So I'll explain all this in detail in different settings, but this is the general picture. So the reason why this is very natural is because these lax integrable field theories have an underlying lax matrix, so some sort of matrix which depends meromorphically on a spectral parameter. And the idea is that this comes from the gauge field in that gauge theory. So the rough idea, and I'll give many examples of this throughout the lectures, the rough idea is that the lax matrix, which is some matrix or Lie algebra valued object, which depends on the space-time coordinates, so x, t, and potentially higher coordinates, and some complex parameter z. So z is some complex parameter. So this is the lax matrix, and this will come under this correspondence precisely from the gauge field. So there'll be some gauge field in the gauge theory. So this is called A. And it depends also on the space-time coordinates and on this extra coordinate z, which parameterizes a patch on the Riemann surface. So here, this spectral parameter comes sort of, it's auxiliary, and there's no really canonical way of understanding where it comes from. The gauge theory provides a very natural explanation for where the spectral parameter comes from, because it's this extra coordinate on which the gauge theory lives. Okay. So this was first understood in 4 dimensions by Costello, Witten, and Yamazaki. So 4 dimensions meaning d is equal to 2. So d+2 is 4, and we're talking about two-dimensional field theories. So what I want to do to simplify the framework is to think about a nicer toy model, which is easier to understand, nicer in the sense that it's easier to understand, where the dimension of the field theory is one dimension. So there's one time dimension. So I'll be talking about integrable systems, finite dimensional integrable systems, and they will come from a three-dimensional field theory. Okay, so then we'll move up in dimensions. So the first talk will be about this three-dimensional theory. The plan is lecture 1 is D equals one dimension. So more precisely, if you have a 1D integrable field theory, that's the same thing as an integrable system, finite dimensional integrable system. So it has finitely many degrees of freedom. So let's say the degrees of freedom are some coordinates qi depending on time. So that's the one time, one dimension is the time, and then coordinates pi, conjugate coordinates pi. So these are the degrees of freedom for some set numbers I equals 1 to capital N, so n particles. And the way to describe the integrable systems with these degrees of freedom is to think about a three-dimensional integrable field theory called mixed BF theory. Okay, and then following this general principle, if you want to describe a one-dimensional system, so on R, then the theory, the integrable field theory, the gauge theory lives on R cross the complex plane, for example. Okay, so the idea is that this will be, the geometry underlying these gauge theories will be some line Cartesian product with a Riemann sphere. Okay, so this is R cross CP1. Okay, and then the second lecture will be increasing the dimension. So I will talk about two-dimensional integrable field theory. So this is a much more familiar context, and there are experts on this in the audience, particular Yamazaki, who initially developed this with Costello and Witten. So the second talk will be about two dimensions. So in D equals 2, sorry, 2. So this will be D equals 2. So here we're talking about two-dimensional integrable field theories. And they can live on various spacetimes. So on the spacetime is called M, but we can take, for example, R2. So this is a non-compact spacetime. Or a nice example to consider also is R cross S1, so the cylinder. So we compactify the spatial direction. So here the degrees of freedom are some fields, pi I, which depends on space and time. A bunch of fields from labeled by I equals 1 to N. And the gauge theory that will describe these integrable field theories will be this celebrated 4D Chern-Simons theory. And the reason I want to start with this 3D mixed BF theory is because a lot of the things that we'll discuss in this 3D case will go over quite naturally to the four-dimensional setting. They'll extend fairly naturally, but it's a bit more complicated. So that's why the toy model in 3 dimensions is nicer. So these are theories on M, whatever manifold you chose in 2 dimensions, cross CP1 or C. So the picture is some plane or a cylinder, and this will be Cartesian product with the Riemann sphere. Okay. And finally, the third lecture will be a bit more speculative. So this is the dimension where things are less understood. So I'll present a way of thinking about 3-dimensional integrable field theories. And in particular, I'll talk about 3, but you can then go on in higher dimensions using the same principle. So in 3 dimensions, we want to describe a notion of 3-dimensional integrable field theories. And they are on, for example, M equals R3. And so there are various candidates for describing these integrable field theories. So one of them, which I'll talk about, is 5D 2 Chern-Simons. I'll explain this in the third lecture. Again, it's on M cross some Riemann surface. And then there's alternative candidates. So you could also use 5D, what's called partially holomorphic. And I'll describe the differences and how they, they describe different notions of lax integrability. I'll come to this later. So partially holomorphic Chern-Simons. And this is again on M cross C. Okay. Really M cross CP1 here. Okay. So the picture here is you have a 3-dimensional volume on which you want to describe your integrable field theory. So this is the volume on which the three-dimensional theory lives, and then the gauge theory will live on 2 extra dimensions by taking the Cartesian product with a copy of CP1.
Excuse me?
Yes.
Maybe I have missed it, but
Sure.
What is the 3-dimensional IFT example?
I'll give examples in the third lecture. So here I'm just outlining the plan of the lectures. I will come to this in detail in the third lecture. Yeah.
I see. Thank you.
Any other questions? So feel free to interrupt me at any point with questions. Okay, so this is the plan. And if there are no questions about the plan, let me start with the first topic for today, which is these one-dimensional integrable systems or finite-dimensional integrable systems, and how they're described nicely in terms of this 3-dimensional mixed BF theory. So I was told to be fairly basic in the first lecture, so I will start with reminding you, if you're not familiar with the lax formalism for describing integrable systems. So let me start with describing finite-dimensional integrable systems. And explain, if you've never seen this before, what the lax formalism or what are lax pairs for such systems. So if you have a dynamical system, so on some phase space T star M, let me call it curly M because I have this M which is different. So curly M. So this is some n-dimensional manifold where n will be roughly the number of particles. And so with some fixed Hamiltonian describing the dynamics on this phase space, capital H. So we say this is lax integrable. So there are various notions of integrability, even in one dimension. Lax integrable means that its equations of motion take the form of a lax equation. Meaning the equations of motion are, there is some matrix L, which depends on some auxiliary spectral parameter, so some complex parameter, and its time derivative, so its motion with respect to the Hamiltonian. So what this is equal to is the Poisson bracket with the Hamiltonian. Right, so this is some matrix which is meromorphic. It depends meromorphically on the parameter Z, and it packages together the degrees of freedom or the coordinates on this cotangent manifold. I'll give an example in a second. The time evolution is the Poisson bracket with the Hamiltonian, and to be of the lax form is that this lax matrix evolves as a commutator with another matrix. So the evolution of L is isospectral. Its spectrum doesn't change in time. Okay, so if the evolution of this matrix L is a commutator, then we say that, so if the equations of motion can be rewritten in this form, we call the system lax integrable. Okay, and these are the systems which can be described using this gauge theory 3D mix BF. So first of all, why is it interesting to have equations of motion in this form? So the point is, because the right-hand side is a commutator, it tells you that the spectrum of the matrix L does not change in time. So it allows you to build lots of integrals of motion by taking spectral invariance of the lax matrix. So first, let's say this lax equation is for some Lie algebra valued meromorphic function. So L of Z. And its components, the matrix components of this function, are living on the phase space. Okay, so the whole point of having an equation of motion written in this form is that you can produce lots of integrals of motion. Because if you take any invariant polynomial, so for any G invariant polynomial, so I chose here Lie group G, sorry, Lie algebra G, and this capital G is its corresponding Lie group. So if you pick a G invariant polynomial, so that's a function P on the Lie algebra, which gives back a number. And the G invariant means that P of the adjoint action on some Lie algebra element is the same thing as evaluating the polynomial on the element itself. So the function P doesn't depend on it's invariant under coadjoint action. So this is for all X in the Lie algebra and little g in the group. Okay, so for any such invariant polynomial, we have that if you evaluate the polynomial on the lax matrix, so this polynomial takes in something in the Lie algebra, the lax matrix is valued in a Lie algebra, so we can think of it as a matrix Lie algebra or more general. So if you evaluate the polynomial on the lax matrix, so this is it's a function that depends on Z, and the point is that this will be invariant in time. Okay. Is this clear? Or do you want me to show why this is true? So for example, for a matrix Lie algebra, you can just take if G is equal to SLN, then you can take just P is some trace of any power x to the m. This is an invariant polynomial. And so for any integer m, if you take the trace of some power of the lax matrix, this will be an invariant function. And the invariance, the fact that this doesn't evolve with time, is a direct consequence of the fact that L itself is evolving as a commutator. Yeah.
Excuse me, what's the relation of Lie algebra K with your symplectic manifold?
So there's no relation.
No relation.
No.
So it has nothing to do with your choice of.
No, so that's the key point, is that usually integrable system, there's some auxiliary Lie algebra that comes from nowhere. And there's some spectral parameter dependence that comes from nowhere. And the gauge theory gives sort of an explanation of what this Lie algebra is, why it comes from the gauge theory. And this comes from the additional 2 dimensions of the gauge theory. So in the standard lax formulation, the Lie algebra is just completely pulled out of thin air. There's no reason for it to be anything related to the manifold M. Yeah. I'll give examples just now. It's completely ad hoc, the appearance of this lax matrix and the dependence on the spectral parameter. So the Lie algebra has nothing to do a priori with the manifold.
Okay, so once given the Hamiltonian, it is non-trivial to find
It's
such
very
a gauge.
non-trivial, yeah, yes.
Okay,
Yeah, it's very non-trivial. Yeah, you have to basically do some clever guesswork. Okay, and the machinery of these gauge theories is they allow you to produce lots of integrable systems very systematically. Okay, any other questions? Okay. So one more thing is that usually the Hamiltonian is given by particular polynomial, which is the coming from the an invariant bilinear form on the Lie algebra. So this is very often the case. So let me just briefly mention this. So typically H itself, which is an integral of motion, it's the Hamiltonian. It doesn't evolve in time. So this is contained so a way to form an invariant polynomial is to take the invariant bilinear pairing on the Lie algebra. So let me say this thing here is the invariant bilinear pairing. So you take a bilinear form on the Lie algebra valued in C. So like the killing form, this is, or trace of x squared. This is an invariant bilinear pairing. So given such a pairing, you can take the lax matrix in both entries. Okay, so the Hamiltonian H is contained in there, meaning that if you expand this in powers of Z, one of the coefficients will be the Hamiltonian. Okay. So let me give you an example. So let's take the Toda chain. I'll give two examples. The first one is the closed Toda chain. Or also known as the SLN hat, affine SLN hat, Toda chain. So the reason it's called closed is because the Dynkin diagram for the Lie algebra SLN hat is a closed diagram. So the closed Toda chain is associated to this Lie algebra. So what is this described by? This describes n particles. So we fix coordinates qi and pi. So I equals 1 to n on the cotangent bundle of Rn. So qi is our coordinates on Rn, and pi is our coordinates on the fiber T star. And because it's closed, there's some periodicity condition as well. So we set, so first of all, for convenience, we define Q0 equal to Qn. So if you go too far down in the labels, so the labels are from 1 to n. If you go too far down, if you go to 0, you go back to the top. Okay, so it's periodic in that sense. The 0th coordinate is the nth coordinate. Same thing for the momenta. So I can say P0 is equal to Pn. So it's a periodic Toda chain in this sense. And also, if you go too far up, if you go to n plus 1, then you get back to P1. So Qn plus 1 is equal to Q1, and Pn plus 1 is equal to Pn. P1, sorry. Okay, so this is just the statement that the Toda chain is closed, or this is also called sometimes periodic. Okay, so there's some sort of periodicity in the coordinates. The nth particle will actually be close to the first particle, just like the first is close to the second and so on. So there's some sort of ordering on the particles, and there's a periodicity in their labeling. Okay. So given these coordinates, the equations of motion for the Toda chain, I'll write it in phase space variables, and then in the more recognizable second order form, just involving Q's. So then the equations of motion read, so the time evolution of Qi is just the conjugate momentum, and the time evolution of the conjugate momentum is some sum of exponentials. So e to the Qi plus 1, sorry, I minus 1 minus Qi. So the two successive particles, Qi plus 1, Qi minus 1 and Qi, you take their difference in the exponent and then minus the exponent of Qi minus Qi plus 1. Okay. And if you substitute the first equation into the second, you can eliminate P, and you get this second order differential equation, dt squared Qi is equal to e to the Qi minus 1 minus Qi minus e to the Qi minus Qi plus 1. So this is the Toda equation. Okay. And so the reason this is integrable is because there's you can write down a lax matrix. So I need to choose a Lie algebra. And because, so here there are different ways of proceeding. One way is, as I'll write it, you can write down an n by n lax matrix. Because there are n particles, it's natural to produce an n by n lax matrix. There's another version which involves 2 by 2 lax matrices. So this is, you see, there's a choice, and there's no natural answer to what is the Lie algebra. It's completely ad hoc. Yeah. So I can produce a lax pair for this. So the lax pair, which is 2 matrices L and M, is given by, so here the Lie algebra is G is equal to, let me say GLN, and Z is some complex parameter. So I can write this down using the basis of GLN. So I can write L of Z is equal to some sum of diagonal elements, so sum from 1 to n of Pi over Z times the diagonal matrix II. So this has got entry 1 in the II component and 0 everywhere else. So it's one of the basis elements of GLN. And the coefficient is Pi over Z. And then I have some off-diagonal elements. So I equals 1 to n of the difference of exponential of the differences, e to the Qi minus I minus 1 over Z squared. And this is off diagonal e to the I plus 1 I. So here there's a convention that if I write e subscript n plus 1 n, so if the index in these, so there are 2 indices on the e sub ij. If either of them is bigger than n, then I make it 1. So it's the same as in the identification of the coordinates. E to the en plus 1 n is the same thing as e1n. So here I'm using the convention that en plus 1 n, which would be for the nth index. This is the same thing as e1n. Okay, I'm using some periodicity in the indices. I'll write it out in matrix form so it's more recognizable. And then plus, same thing, an off-diagonal matrix, but it's below the diagonal. So it's ei I plus 1. And it's just got coefficient 1. So let me write it in matrix form. So it's got P1 over Z, P2 over Z, all the way down to Pn over Z along the diagonal. And then off the diagonal, so the E21 component will be given by this expression. So E Q1 minus Q2 over Z squared. So this is the E21 component. Then there'll be E32 component is E to the Q2 minus Q3 over Z squared all the way down. The last one here is E to the Qn minus 1 minus Qn over Z squared. And so this is the n I is equal to n minus 1. And then the nth one, as I said, it's up here because it's the 1n component. So you get to the top corner. This is e to the Qn minus Q1 over Z squared. Okay, so the bottom diagonal and this top entry is the second sum here. And then the last sum is a bunch of ones, but it's above the diagonal. That's E12, E23, so here, all the way down to here. And then also, when I is equal to n, I get En comma 1. So it's down here. Okay, and everything else is zeros. So this is the lax matrix L, and then I also need to tell you what the matrix M is for the lax pair. So let me just write it in this more abstract way. The matrix form is very similar. Let me write it in the basis of GLN. So M of Z is in fact just this middle component. It's identical to this middle sum. So it's I equals 1 to n of e to the Qi minus Qi minus 1 over Z squared e I plus 1i. Okay, so it's basically the same matrix, but there's no diagonal. It's zeros on the diagonal, and there's no ones above the diagonal. It's just the exponentials. So this is the matrix M. So you can check that if you compute the time derivative of this object and you compare it to the commutator of L with M, you get exactly the Toda equations in the form I raised with up there in this form. Yeah. Okay. So secondly, what's the Hamiltonian? So this is related to the comment I made before. So note that if I take a half times the trace of lax squared, so trace of x squared is the invariant bilinear form on GLN. And if I plug the lax matrix into it, then I get 1 over Z squared, a half sum of the pi's squared, plus the sum I equals 1 to n of e to the Qi minus Qi minus 1, I plus 1, which is literally just the Toda Hamiltonian. So this is 1 over Z squared times H Toda. Okay, so the Toda Hamiltonian is one of the coefficients. It's the only coefficient of this trace of L squared. Okay. So that's the Toda Hamiltonian. And what this Hamiltonian does is it generates time evolution. On the phase space T star Rn. Okay. So the time evolution of any function of P and Q, this is by definition the Poisson bracket with the Hamiltonian. Okay. So what's nice is that you don't just have the Hamiltonian, you can get all sorts of other integrals of motion by taking traces of higher powers of the Lax matrix. So trace of L cubed, trace of L fourth. These will give you other independent quantities, which by construction will Poisson commute with the Hamiltonian because they are time independent. They are time independent. So other integrals of motion are given by the coefficients as a function of z of, you just take trace of L of z to some higher power. So let me call it trace of L of z to the m for some m, which is at least 3. Okay. So by construction, these will all be independent of time. Their time evolution will be 0. Okay. Okay. Any questions about this example? Yep. No.
But sorry. If I give you a random Hamiltonian, how do you find possibly a Lax pair? Is there any
Lax pair?
Yeah, or like what kind of structure do you like if the Hamiltonian has what kind of structure, then can I expect that maybe Lax pair or some sort of integrability may exist?
No, I think it's
Well,
purely guesswork and intuition that gives rise to these Lax matrices. People came up with them many years ago, but it's just a lot of clever guesswork. I don't think there's a systematic way. Given a Hamiltonian, first of all, it's not clear whether it's integrable or not. It's very hard to determine whether it's integrable. Yeah. What you can do is build lots of models by essentially the story I'll tell you in these lectures is a way of producing lots of models. And these are by construction integrable. And then among these large families of models, you can recognize some that you're familiar with, or you can pick out a Hamiltonian that you might be interested in. But if you give me a Hamiltonian, there's no way of telling.
Okay.
This is a very complicated question.
Okay. Yeah. Thank you.
It's like solvability of. So you need some sort of Galois theory for differential equations. Like, is this equation solvable in the sense of can you find a general family of solutions? The answer is we don't know because it's a very complicated question. Yeah. Okay, so here I'm just telling you that you basically from some clever guesswork that this is the Lax matrix. If you were to just give me the Hamiltonian, I wouldn't know how to produce this Lax connection or this Lax pair. Okay, so another example which will actually be very closely related to this, but is more general in some sense, or in a precise sense, is this important family of Godin models. So this one is described a bit more abstractly, but what I'll show you is that the Toda model is an example of a Godin model. So this is a more general family, which includes, if you sort of allow some generalization I'll talk about, includes the Toda closed chain. So what we do is we fix some elements, lambda 1 up to lambda n, so lambda capital N, in the Lie algebra, which from now on I'll always assume is identified with its dual. So this is a finite dimensional Lie algebra, which I identify with the dual via this non-degenerate invariant bilinear form that I've chosen. So I assume I've chosen an invariant bilinear form in the Lie algebra, and it allows me to identify the dual with the Lie algebra itself. And where this Godin model lives on, so this it lives on the following symplectic manifold. So I want to consider a product of co-adjoint orbits. So let me explain what those are. So it's a product of manifolds O lambda I. So each of these O lambda I's is a technically co-adjoint orbit. But because I'm identifying the Lie algebra with its dual, the co-adjoint orbit is the same thing as the adjoint orbit in the Lie algebra. So co-adjoint orbits. So I'm taking a product of these co-adjoint orbits. Each one is this manifold. O lambda I is defined as just the orbit of one of these fixed elements. So HI conjugated, conjugation of lambda I by HI. So this is for some HI in the Lie group. Right? So this is just a point in the orbit of lambda I. I take any possible conjugation of the fixed element lambda I by some Lie group element, and I get to some point on the orbit, which is labeled JI. So JI is just some point on this orbit. Okay. So it's slightly more abstract, phase space. So this orbit itself lives in G, or if you prefer in the dual, it's a co-adjoint orbit, abstractly. And I take their products. So the point is this has a natural symplectic structure. There's a natural phase space on this product, or in the individual orbits themselves. So this is a symplectic manifold.
Excuse me, there are capital N and small n. Are the same or different?
It's the same. Sorry.
Okay.
Yeah, it should be capital N. Thank you. Yeah, and not the same as the little n I had before for SLN. Okay. So here it's all big N. The number of orbits is big N. So this is a symplectic manifold. With Poisson bracket. Given by. So here I'll be using some tensor notation. So Ji sub 1. So Ji is an element of the Lie algebra. It's a point on the orbit. So if I have an element in the Lie algebra, then I use the notation x sub 1 to mean x in the first tensor factor, and then x sub 2, 2 underlined or 1 underlined, means x in the second tensor factor. So this allows me to write Poisson brackets between different components of the Lie algebra elements. So if I pick a basis of the Lie algebra, I have a bunch of different components for this Lie algebra element, and I can write down in a very unified way the Poisson brackets of all these different components using this notation. So Ji tensor 1 with Jj tensor 2. This is, I'll explain if you want explicitly afterwards. So the way to write down this Poisson bracket in a nice way is like this. So minus the Lie bracket with the split Casimir, and then Ji2 delta Ij. So this is for I equals 1 to n. So let me say with C12, this is called the split Casimir. So it's IA tensor IA for some dual basis of the Lie algebra. So where IA is a basis of the Lie algebra, and I superscript A is a dual basis. So dual basis of G is relative to the invariant bilinear form that I've chosen. So dual basis means that IA with IB is delta AB. Okay. So maybe if you're not familiar with this notation, let me just explain in more explicit terms in components what this means. So in components, I can write this element Ji of the Lie algebra, which is a point on the orbit. I can write it in a basis as Jia. This is the component along the element Ia. Okay. And so I can write this Lie bracket in components. So we have, so first of all, well, let me write it. So the Lie bracket, this Lie bracket is really the same thing as writing Ji component A with J component B. Okay, so I told you this was a sort of fancy way of writing all the Lie bracket or Poisson bracket of all the components together. So indeed, these are all the different components of the two points on the orbit, Ji and Jj. So their bracket is given by FABC JCI delta Ig. Okay. So every single component of Ji, I can tell you its bracket with the component of Jj, and it's given by this expression. But this is sort of a nice packaging together of all the components. Okay, so if you want to recover the expression above, what you do is you multiply by Ia tensor Ia or tensor Ib. So on the left-hand side, you get Jia with Ia. That's the component. This is the matrix element Ji. And then Jj is Jjb, Ib. So they're sort of packaging them together in a tensor product. So this Lie bracket lives in G tensor G. This is this is a function. Both sides are numbers. Okay. Is everyone okay with this notation? Okay. So this is a very important bracket, which I want to give a name to. So I'll call this star, this relation. And in components, it's really just this. I'm telling you the brackets of all the different components of the points Ji and Jj on the orbits O lambda I and O lambda J. So first of all, note that if you're on different orbits, the components Poisson commute. So there's a delta Ij. So the orbit is really a product of symplectic manifolds. So the Poisson bracket of a coordinate on one of the orbits and a coordinate on another orbit, they Poisson commute. But on a given orbit, so on a fixed I, I'm looking at the same Ji, but I'm looking at different components of it. And these different components have these Poisson brackets. Okay. So now what I do is to define the Godin model is I pick, so this is defining the symplectic manifold. I haven't told you the dynamics on this manifold. So it's just a symplectic manifold. And now I want to describe the dynamics. So what I do is I pick any distinct points Zi in C. And rather than write down the Hamiltonian and then tell you it's integrable because it has this lax matrix, I will write down the lax matrix to begin with and define the Hamiltonians from this lax matrix. So I define the lax matrix of the Godin model as follows. So L of Z is just a linear combination of the different Ji's. So I sum over I equals 1 to capital N, the Ji over Z minus Zi. Okay, so the JIs were points on these different orbits. There are n of these orbits, and I just collect them together as one current or as one rational function with residues at the ZIs, and the coefficient of these residues is just the current JI. So if you want to write it more explicitly, it's sum from I equals 1 to capital N of HI lambda I, HI inverse Z minus ZI. Okay, so these are really the coadjoint orbits as residues of the lax matrix. So it's collecting together the different degrees of freedom of the manifold. In the same way as in the total lax matrix, the total lax matrix collected together the PIs and the QIs as its different coefficients. Here, the different residues of the lax matrix at each ZI is giving you the components of the lax matrix, the components of the coadjoint orbits. Okay. And then from this lax matrix, I can tell you, well, first I need to tell you, let me tell you the Hamiltonian. So the Hamiltonian is defined by fixing another point. So W, I fix another point on the spectral plane, and some polynomial. So I choose a G invariant polynomial P on the Lie algebra. Then the Hamiltonian is just P of L of W. Then I define the Hamiltonian as P of L of W. Okay, so this is it's a number, or it's a function on the phase space, because L is built out of the coordinates on the symplectic manifold. I just evaluate it at a point W, and then plug this L of W into the polynomial P to produce some number, some C-valued function on the symplectic manifold. So this is some function from the product of coadjoint orbits into C. Right? It depends on the coordinates on the symplectic manifold through the lax matrix, and it's a function on the symplectic manifold. Okay, and so it's Poisson bracket with this Hamiltonian gives me the time evolution of the system. So this is a slightly more abstract system because you don't get to see explicitly anything in terms of coordinates Pi and Qi, but I'll show you in a second that the total Hamiltonian is exactly an example of this kind of setup, slightly generalized. And then you can see maybe more concretely why Ji is a coordinate on a manifold, on a symplectic manifold. One thing I need to tell you first is using this important Poisson bracket relation. Yeah. NEP, yeah. NEP works, and typically what you do is you take the invariant polynomial. So sorry, the invariant Balinet pairing, this one. And you take L of W paired with L of W. Then it's called the quadratic Godin Hamiltonian. But really, NEP defines a Godin Hamiltonian. I should label the Hamiltonian by P if you prefer, H sub P. It depends on the Hamiltonian. It depends on the polynomial you chose. The standard choice is to take P is this invariant polynomial, the quadratic one. Yeah.
So for every choice of H or every choice of P,
yeah.
Are you saying that there exists a Lax pair, or you're saying that?
So remember that the Lax pair.
Oh, sorry, Lax pair is already given. Sorry.
Yeah. Yeah. The Lax pair describes a whole bunch of Hamiltonians, because each of the flows which Poisson commute with each other, they are different dynamics on the same symplectic manifold. So I'm just saying that these H's labeled by P, they all Poisson commute. They are all possible Hamiltonians you can choose in the system. because, and with respect to any of them, the system is integrable because, yeah, I should probably, let me say, so if I picked a different polynomial P, if I pick two polynomials P and Q, then these corresponding Hamiltonians, they Poisson commute. It's probably just simpler to pick a given P. So let me just say, usually, just take P is this invariant Balinear form. So it's a quadratic polynomial. Then H is called a quadratic Godin Hamiltonian. But the point is that there are other Hamiltonians. There's a cubic one, which comes from taking, if you take SLN, take the trace of the Lax cubed, this is another Hamiltonian. So there's a whole bunch of Hamiltonians. And the simplest one is what's called the quadratic Godin Hamiltonian, and it comes from picking P to be the quadratic bilinear pairing. But the point is, the system is integrable with respect to any of them because, well, because of the relation I'm about to write. So from this star relation, this important relation, so this star relation, which was the Poisson bracket on the symplectic manifold, this is equivalent to what's called the Lax algebra. So if I take the Poisson brackets of the Lax matrix at two different spectral parameters, L of Z prime and L of Z, and I take these with subscripts 1 and 2. So again, this is the tensor notation, which allows me to write the Poisson bracket of all the different components of the Lax matrix, which is Lie algebra valued. All its different components are different values of Z and Z prime. They are nicely packaged together into this one Poisson bracket. So C12 over Z minus Z prime, L of Z prime minus L of Z at 2. Okay, so this is just a rewriting, literally a rewriting of the bracket star. So this is really equivalent to star. The way you get back to star is you just take the residues on both sides at Z prime equals Zi and Z equals Zj. So if I take, so to get to star, you take the residue at Z equals Zi and the residue at Z equals Zj. If you do this exercise, you'll find that on the left-hand side, you get Ji and Jj, the residues of the Lax matrices. And on the right, you'll get the right-hand side I had before for the star equation. So this is just a repackaging. But the point I want to make to answer the question is that any of these Hamiltonians, they Poisson commute. If you take, because this Poisson bracket is a commutator, so this implies that the Hamiltonian associated to some polynomial P and the Hamiltonian associated to some other polynomial Q, they will Poisson commute. Okay, so if you think of this as the Hamiltonian, then this is an integral of motion. If you think of that as the Hamiltonian, then this is an integral of motion. So depending on which one you choose as your Hamiltonian, all the other things that you can build from the Lax matrices will be integrals of motion. Yeah. The dynamics is just induced by one of the Hamiltonians. You pick the one you like, and then the other ones are just integrals of motion for this flow. Yeah. Okay. I have half an hour left, so I think I've been going quite slowly. So let me just say that, yeah, if you pick one of these Hamiltonians, H, then under the time flow with respect to this Hamiltonian, so under time flow by the Hamiltonian H, we get that the time evolution of the Lax matrix, which is just the Poisson bracket of the Lax matrix with H. This is the commutator of M with L, where M is the gradient of P over Z minus W. So let me give you an example of what the gradient is rather than defining it in general. So if P of X is the trace of X to the N or X to the M, then the gradient of P is the function M X to the M minus 1. So it's matrix valued. So here I'm working with matrix Lie algebra. So this polynomial function P is a function that takes a Lie algebra element and gives back a number. But then when I take the gradient, I get the gradient takes a Lie algebra element and gives back another Lie algebra element or a matrix. And so the gradient is just taking the derivative with respect to the argument. Okay. So I don't have time to explain why Todo is of this type. If you want to ask me afterwards, I'm very happy to explain. But let me just move on to 3DBF because I have half an hour. So I want to really show you how this Godin model comes about from 3D mixed BF theory. And it's a very simple story. So I can tell it to you in half an hour. The key things to remember are so this is the dynamics of the system where the Lax matrix is given in this form. So this is the key equation to remember. Lax matrix is this meromorphic Lie algebra valued function, and its time evolution is given by this Lax equation, okay, where M is also of a particular form. So this M you should also keep in mind. And I want to produce this kind of dynamics from some gauge theory. And this example will be really sort of a very simple toy model for what happens as well in the higher dimensions, why gauge theory is capable of producing Lax formalisms. So 3D mixed BF theory. So I want to describe this dynamical system with the Lax matrix I just erased from a gauge theory. So let me write down the action, and we'll see why this is the right action. So I want to, in other words, produce this as a variational equation. This should be the dynamics or the Euler-Lagrange equation for some gauge theory. So consider the following gauge theory with action S3DBF, which depends on two fields A and B, and the action is given just by the integral of some field B paired with the curvature of some field A. So this is a field theory on R cross CP1. So what are A and B? A and B are smooth G-valued fields. So A has two components, a T component along dt and a Z bar component. Along dz bar, and B has just a dz component. So B has a single component called bz, which is a function times dz. Okay. So here z is just some coordinates. I'm really working with C for simplicity. So I'm working on one copy of C. I'm ignoring the point at infinity. And so these are just two fields which A has two components, AT and AZ bar. They both are functions on R cross C. So T is a coordinate on R and ZZ bar are coordinates on C. And B is also a function on R cross C. Okay, so I told you this is a gauge theory. It's very easy to check. So this is a gauge theory if I let A transform as a gauge field and I let B transform as a by conjugation. So there's some gauge invariance. So for some G, which depends on Z, Z bar, and T, so this is some parameter for my gauge transformation. So let me say for G, such a function, I let AI transform as a gauge field, so by G AI, G inverse minus DI, GG inverse. So AI, I here is either T or Z bar, right? A has two components. So I can transform as a gauge transformation like this, as a gauge connection. And then BZ transforms by conjugation. So G, BZG inverse. Okay, so B transforms by conjugation. And if A is a connection transforming like this, then the curvature transforms by conjugation. So this F, it has really only one component appearing here because it's a three-dimensional manifold. There's a dz here, and this has to have a dt and a dz bar. So there's just one component, dz, ft tz bar. That's the only component, and this transforms by conjugation. So f tz bar transforms to g f tz bar g inverse. And then because this pairing is adjoint invariant, B transforms by conjugation, F transforms by conjugation, so the whole pairing is invariant. Right? So this is really invariant under that transformation. Yeah.
Excuse me. Z depends on G depends on Z.
Yes.
So it may create a Z component, right?
Yes, but I'm just looking at the T and Z bar component. If you like this as a partial connection, if you okay, let's suppose you create a dz bar component, dz component, because there's a wedge product with B here, and B is a dz, it drops out. It doesn't matter.
Yes.
Okay. Okay, but that's a good question. So this kind of thing happens as well in the 4D theory. So I'm allowed to look at partial connections, which only have dt and dz bar components. The dz component drops out because it's wedged with B, which is a dz form. Yeah. Okay, so that's the theory. And now the question is, why does this describe integrable field theories or integrable Lax equations? Well, the aim was to describe this through the dynamics of the gauge theory. So let's look at the equations of motion. And the equations of motion should somehow look like the Lax equation. So what are the equations of motion? So I can look at the equations of motion for B. That's very easy. So for B, I get just the curvature of A. So I get dz A T, dz bar AT is equal to dt AZ bar plus AT with AZ bar. So this is just the curvature of A, right? If you vary with respect to B, you just get f of A. And if you vary with respect to A, it's easy to see. You get two components. So you get dz bar of bz is equal to commutator of bz with az bar. And then the dt of bz is equal to, let me write it as minus az, minus at with bz. Okay. So that's the equations from varying the action with respect to A, which is just 2 lines of calculation. So now we stare at this and we see this last equation looks very interesting because it tells you that the time evolution of Bz is a commutator of Bz with something else, which looks very much like a Lax equation. So this is one of the key points. So this looks very much like a Lax equation. But it's only superficial because there are lots of differences as well. So it looks like a Lax equation where, so let me say with L is Bz and M would be minus AT. Okay. But the problem is that A and BZ, AT and BZ are smooth fields. They don't depend meromorphically on Z. Also, there's no relation at all between the two. But if you remember the expression I wrote down for M, it should be expressed in terms of L. It should be gradient of P evaluated on L of W. But AT has nothing to do with BZ. It's just a separate field. So, so there are several problems here. So let me just write out the problems. So first issue is that B, let me write it in full, B of T is Z bar. So it depends on these 3 coordinates, and also AT of T Z bar. They depend smoothly on Z and Z bar. Okay, so that's not nice because I want meromorphic expressions. So this is easy to solve. Let me solve this problem first. So we remember that we're dealing with the gauge theory because we have this gauge invariance. So if we can find a nice gauge where the dependence on Z and Z bar become meromorphic, then we can solve this issue. And it turns out that there's a very nice gauge, which is simply to go to the gauge where AZ bar is equal to 0. Because if we can set AZ bar to 0, every term on this right-hand side will be 0. And the top 2 equations tell you that dz bar of AT is 0, it's holomorphic, and dz bar of BZ is 0, it's holomorphic. Okay, so this problem is solved by going to the gauge AZ bar equal to 0. So, but we can use gauge invariance of the theory to impose gauge fixing condition that AZ bar is equal to 0. So locally, and in fact on C, I can always go to this gauge by solving the equation AZ bar is equal to G inverse dz bar G. So you find the gauge parameter G that brings you to the gauge AZ bar equal to 0. So I can freely move to that gauge. And in that gauge, the top 2 equations now tell me that AT and BZ are holomorphic, okay, which is very nice. But it's too nice because I wanted them to be meromorphic. So it's gone too far. We now got purely holomorphic A and B, whereas I should have had meromorphic A and B. And also, as I said, A does not really depend on B. They're just 2 independent fields. So there are still 2 issues. So let me just say now we have dz bar of AT is equal to 0, and that's also equal to dz bar of BZ. So AT and BZ are holomorphic. Okay. In Z. So let me call them L is equal to BZ. So it's now holomorphic. It depends on T and Z in a holomorphic way. And AT, sorry, I call M is minus AT, which depends now holomorphically on Z. So the issue with L and M is that we want them to have poles. So first of all, we want L and M to have poles. And secondly, so poles in C. So L should have poles at the zi's and M at this point W that we put by hand to define the Hamiltonians. And M should be related to L. They shouldn't be independent fields. So recall that M of Z is equal to this gradient of P at L of W over Z minus W. So if you know L, then you find exactly M. Okay, so the way to resolve this issue is to modify 3D mixed BF by adding what are called defects. So we're going to modify the theory not in the bulk. So the theory will stay the same almost everywhere, but on some line defects, we're going to modify the theory. And this will introduce poles in the... let me keep these equations. So let me add, so I'll keep this because I'll come back to it, not to have to write it again. So let me add line defects. So adding line defects. This, I claim, will resolve the two issues we have here. So I'll just write down the action. So I now have an action that depends on the two fields A and B, but also on some hj, little hj, which are group valued functions of R. So these are hj are functions on R valued in G. So these are the same things that I used to parameterize the coadjoint orbits. There are hi's, so the orbit was hi lambda I hi inverse. These are the same things. So they're functions of just a point on R. And my action is the same bulk action, because that's what produces the Lax equation. So B paired with f of A. Now I add some defects. So the picture is the following. So we have C and cross R. So I can draw it in 3 dimensions. This is C cross R. And so what I do is add the points Zi, which I had in the definition of the Godin model. So I have capital N points. Let me call them from J equals 1 to N. So what I do is I add some defects. So at each of these points Zi, so let's say Z1, Z2, up to Zn, I add some defect. So the action will be modified at these lines. So there are points on C, but all along the direction of R. So I'm integrating along these lines. So I'm integrating along R cross the point Zj. So this is an integral along those vertical yellow lines. And the way I modify the action on these lines is I take lambda j paired with hj inverse dt plus at hj dt. Okay, so I'm modifying the action along those defects, along those lines. And then I have another type of defect. So these are called type A defects because they just depend on the field A. And then I also added this point W in the Godin model construction. So remember, these yellow lines are the points where the lax matrix has poles. So this will give rise to the poles of the lax matrix. And I had another point W where the matrix M turned out to have a pole, which is the point I used to define my Hamiltonian. I add another defect here. So this defect is, so it's an integral along R cross W. So it's just an integral along that line. And what I integrate is the polynomial P of B of Z along dt. Okay, so this is really just, I'm putting in the Hamiltonian by hand. So the Hamiltonian was P of the lax matrix. We anticipate that the lax matrix will essentially just be B of Z. And so I'm here literally just adding the Hamiltonian, which I called H before. It's P of the lax matrix. Okay, so this is my modification of the action. And if you modify the action, the equations of motion will be modified. And they're modified in a way, so this is why I didn't want to erase these. They're modified just locally on those defects. Everywhere away from these defects, so for any z not equal to those points, the equations are the same. But on those points, you get modifications which come from these new terms. And the modification is the following. So from this term, if I vary the equation with respect to B, then I don't get just this. I get a modification which comes from the last term in the action. So I get 2 pi I, because this has a normalization 1 over 2 pi I, gradient of P at Bz of W. So it's Bz evaluated at W because that's where the action is localized. And times a delta function d of Z minus W. Okay, so that's from this last term in the action. So one modification. I still have these two terms. I have to tell you how to get rid of these. It's not yet clear. Then the second equation, it's the equation of motion for A. So you might think that both of these get modified, but this is the equation of motion from varying AT, and so it gives rise to modification of this first equation. The second one, which we want to keep, it's the lax equation, does not get modified. Just because I added AT, I modify this first equation, and it becomes, it has a new term, minus 2 pi I, sum over j equals 1 to n. So it's the sum over all these defects, so you get contributions from each of them, and you get hj lambda j hj inverse delta of z minus zj. And this is the thing which I called j sub j. So it's a Lie algebra element, which is just a point on the coadjoint orbit. Okay, and these are the Dirac delta distributions localized at the points Zi and W. Okay. So let me explain to you why you can still go to the gauge AZ bar equal to 0. The point is this is still a gauge theory. So I need to tell you about how to modify or how to let Hj transform so that this is a gauge theory. So you just let it transform by left multiplication by the group element G, the gauge transformation parameter. So the point is this is still a gauge theory, even after modifying with the defects. So we still have a gauge invariance. If we let Hj transform as G evaluated at Zj, Hj. So this just means take the gauge field G. So this just means G of T, Zj, Zj bar, Hj. Okay. So if you let Hj transform in this way, then this term is gauge invariant because the connection dt plus at transforms as a gauge connection. the conjugation on the outside by hj will cancel the variation of dt plus a because of this behavior. And this is just still gauge invariant because P is an invariant polynomial. Okay. So we have a gauge theory, so we can still go to the gauge to the gauge AZ bar equal to 0. So the punchline is that in the gauge AZ bar equal to 0, we have the first two equations tell me that dz bar of AT is equal to 2 pi I gradient of P of BZ at W. And then the second equation above is dz bar of BZ. This is equal to minus 2 pi I sum from j equals 1 to n of j delta of z minus zj. And I still have the lax equation. Okay, so I still have dt of bz is equal to minus at commutator with bz. Okay, but then these equations, they're telling you that at is not quite holomorphic. It's holomorphic away. I should have put the delta of z minus w. So dt is holomorphic away from the point w. At the point w, you can use this identity that dz bar of 1 over z is minus 2 pi I delta of z minus 0. Or if you put z minus w, or z minus some point, this is z minus a. So using this identity, this equation tells me that at, let's say minus at, is equal to gradient of P of L of W over Z minus W. So I call this M of Z. And L is just, so if you solve this equation, tells you that L of Z, which I define to be B of Z, this is just given by the sum over j equals 1 to n of j over z minus zj. Okay, so these are exactly the lax matrices, the lax pair of the Godin model, and they solve the zero curve, the lax equation. Okay, so this is just the lax pair of the Godin model. Okay, so we got these as literally the equations of motion of a particular theory, which was this 3D mixed BF theory, modified by two types of defects. So first two equations literally tell us that both of these L and M are meromorphic with the exact meromorphic pole structure that we expected, which depend on the data that we put at the defect. So in other words, the defect is where I put in the information about the symplectic manifold I was working with. So these HJs parameterize the symplectic manifold, which is the coadjoint orbit of this element lambda j. And this symplectic manifold information was put in at the defect along these lines Zj, and it came out as the pole of the lax matrix. And then the dynamics of the theory was put in at this other defect, W, where I chose my polynomial and plugged in this defect, and it told me that the matrix M of the lax pair was given by this particular expression, which we recognize from the Godin model. And the lax equation came out from one of the three equations of motion. Okay. So I'm out of time. All I want to say to finish is that you can basically derive everything else from the Godin model I told you. For example, the Poisson structure of the lax matrix with itself, which was equivalent to this fundamental relation star. You can derive it just by performing a Hamiltonian analysis of this 3D mixed BF theory. And you get that the Poisson bracket of L with itself, after some gauge fixing, so you apply the Dirac reduction procedure to go to this gauge AZ bar equal to 0. And after doing this, you find that the Dirac bracket for this lax matrix is exactly the lax matrix algebra I had before. You can also go to higher genus. You can replace the Riemann surface or the copy of C here by CP1 first, and then by any higher genus Riemann surface. So you get Godin models or integrable systems called Hitchin systems living on Riemann surfaces. And these are all produced by 3D mixed BF theory on R cross the Riemann surface. One thing which is not fully understood in this setting is how different possible realizations of the Godin model, one of which I presented today, which was realizing all these JIs as coadjoint orbits. We know that this is coming from this kind of defect, but there are other kind of Godin models, such as the Toda model. And the Toda model, it's not completely understood yet in this setting what kind of defect it comes from in the 3D mixed BF theory. But in principle, because Toda theory, or the closed Toda chain, as I haven't explained, but I'm happy to explain if you ask me, it's an example of a Godin model, and it should come about from a particular modification of the 3D mixed BF theory along certain defects. So the type of defects to produce specific models is not yet known, but the point is, in this framework, if you find any gauge invariant modification of the theory along lines, that will give rise to particular examples of lax matrices for a given model. So you basically have a framework for producing integrable lax equations by taking the bulk theory, which is 3DBF, as always, plus modifications along certain line defects, and the choice of these line defects will produce various different models. Okay, I think I should stop here. Thank you.
Okay, thank you very much. Any questions? Oh. Please.
Okay, so thank you for your nice lecture. And so I have questions about the pole structures on the Lux pair. So here you assume the simple pole structures for the Lux pairs, but is it possible to generalize the pole structures?
You mean have higher order poles?
Yeah.
Yeah, so Toda is an example with second order poles. And so, I mean, there's some ideas of how to extend the pole structure. So since you're familiar with 4D transimens, this is more like disorder defects where you take the bulk action and you add stuff. I think disorder defects, I don't know if it's been written somewhere. Maybe you know how to produce second order lax matrix.
Yeah, I know, yeah.
Okay, so yeah, we can talk about it. I have an idea as well how to do that. Maybe you've already written it, I don't know. But yeah, I think it's not difficult, but it's not been written in this language, at least, not in the 3DBF theory.
Okay,
yeah.
Thanks.
Any other questions? How about from online participants? Let me ask one question. In the last part, maybe I missed your point. You claim the classification of integrable system is done by classifying the possible defect.
Yes.
Is it right?
Exactly. Yeah. Because the bulk theory always gives you the lax equation.
Yeah.
But then how the lax matrix L and M look like in terms of poles, what their algebraic structure in terms of poles, and what the coefficients of these poles are is purely determined by the defect. So if you like, the classification of lax matrices for lax matrices with Poisson brackets are linear in the R matrix. So the one like the star relation. These are classified by defects which are gauge invariant, which you can add to the bulk equation, to the bulk action. So in this sense,
how about the possibility of changing the bulk part?
Well, if you change the bulk part, there's a risk that you modify the lax equation. The bulk part is sort of designed so that you produce the lax equation, and you want this equation, and these two equations are nice because it tells you that apart from the defects, the AT and BZ are holomorphic in this gauge AZ bar equal to 0. So you really want that, but then you don't quite want it to be holomorphic. You want it to be meromorphic, and that's why you should modify the action at certain points only on CP1. Mm-hmm. So the modification should be local at points on C to produce meromorphic lax connections, right? So I think all of this is sort of forcing you to get 3D BF theory. If you modify that, you'll move away from lax equations and meromorphic dependence on poles. So it's better not to modify this. But if you, because this is gauge invariant, the aim of the game is then just to find other gauge invariant defects you can add. So they should be localized on specific lines. Those lines are at points on CP1 where the lax matrix will acquire poles. So lax matrix acquires poles at these defects, and this additional pole is encoding the dynamics. So everything is localized at line defects, and you don't want to modify the bulk part because otherwise we move away from lax integrability. Yeah.
Okay, thank you. Other questions? So if not, let's thank the speaker again. Thank you very much.
Okay, thank you very much. So I will be talking today about the second part of the story, which is about 2 dimensions. So we've already heard a lot about this in Yamazaki-san's very nice lectures. So I'll also present this, but maybe in a slightly more expanded version in the length of this lecture. So I'll explain in detail the relationship between 2-dimensional integrable field theories and 4D Chern-Simons, and I'll try to stick as close as possible to the parallel story we saw last time about 3D versus 1D integrable field theories. So let me start by describing the relevant notion of lax objects, which in 2 dimensions is this thing called lax connection. So this is the suitable generalization of lax equation in 2 dimensions. So the reason is because we say that a field theory, so a classical field theory, in 2 dimensions is lax integrable if its equations of motion take the form of a lax, take the form of a zero curvature equation. So take the form of a zero curvature equation so this replaces the notion of lax connection, lax equation. So zero curvature is just dl for some connection that depends on a spectral parameter. So d is the Durand differential in 2 dimensions plus half the commutator. So this is for some g-valued 1 form or connection on in 2 dimensions. So for some Lie algebra valued connection. So this curly L has 2 components, which I write as straight L. So it depends on space and time, and also on the spectral parameter. So this is the dx component, L is the dx component, plus a time component, which is m dt. Okay, so in components, you can write this more explicitly as dt of L. So you have a term which is the commutator between L and M from this commutator term, but the differential also introduces another term, which is new compared to the lax equation, which is dx of M of Z. Okay, so if you compare this to the lax equation, you have this extra term now because the lax connection now explicitly depends on space. So you have an extra spatial derivative in the lax connection. So this is a natural generalization of the lax equation. The zero curvature equation generalizes lax equation. And the point is that this still provides you with infinitely many integrals of motion. So you still have the same story that a lax equation or lax formalism provides you integrals of motion. And this is, throughout my lectures, this is the key point is that lax integrability provides you with a generating formalism for integrals of motion. So now you have to work a bit harder. You have a zero curvature equation. You have this new yellow term. So you can't just take traces of powers of L. What you have to build is this thing called the monodromy, or the Wilson line of the connection. So we consider the monodromy matrix, which is the Wilson line of the lax connection around a Cauchy surface or Cauchy curve. So the monodromy is curly M, nothing to do with straight M. So it depends on a particular choice of time, because what I can do is I can integrate the lax connection over a time slice at time t. So this is CT. So here, this is a cylinder where the vertical direction is time and the spatial direction is compact here. Or I can look at two-dimensional R2. So I have X and T still, but now my Cauchy surface is just a line extending across the non-compact direction. So given this choice of constant time curve, I define the monodromy at this time t as the path ordered exponential of the lax connection. So L of t x z dx along this curve CT. So because the curve is purely along the x direction, there's no m component in the integrand. And the point is that this object, if you ask about how it evolves in time via the lax equation. So its time derivative is a commutator with something, and therefore this thing has conserved traces. So a simple way to see this is, let me do it here. So if I take any central function, so a function on the group, so I should have said this is valued in the Lie group, because the lax is valued in the Lie algebra. So if I take some function from the group to C, which is central, meaning that it has the property of the trace, it's cyclic. So f of gh is equal to f of hg for every g and h in the group. Then f of the monodromy is a conserved quantity. So we have that this, so you can think of just f as being the trace. This central function of the monodromy is time independent. Okay. And one way to see this is, as I said, you can show that this satisfies a lax equation, this m curly m, or you can think about breaking up this contour into various pieces. So let me do it here. So I want to relate m at a time t to m at a different time, t prime. So I can look at the curve CT, and then I look at a later curve CT prime. And then I can pick a point on this curve and connect them together by a line that goes back and forth. So let me call this, so let's say this is a curve UTT prime. So it's a line that goes from a point on the curve CT to a point on the curve CT prime. And it goes, I call it UTT prime. Then you can show that m evolves by conjugation by the path ordered exponential along these vertical directions. So the point is that m of t prime z is equal to curly u of tt prime, curly m at t, and then curly u of tt prime inverse, where this curly u is just the path ordered exponential along the yellow curve. So this is path ordered exponential along utt prime. of the lax. So really, this is the curly L. So let me write it as part of that exponential of the one form L. Okay, along this time-like direction. And so if I now take apply f, then because f is a central function, the u inverse I can bring to the other side, they cancel, so the function f of m is invariant under time. Okay. So the lax formalism is a nice framework to produce integrable field theories. So if we can write an equation of motion in the lax form, then by this kind of argument, we're guaranteed to have infinitely many integrals of motion. And the infinite number of integrals of motion typically comes from expanding this f of the monogamy in the parameter z. So f of m is analytic in z, and so we can expand it, and every coefficient will be conserved in time. Okay. Any questions? Okay, so let me give some examples. So I'm going to parallel the examples I gave yesterday. So the first one is a generalization of the Toda chain, which is the sine-Gordon equation, sine-Gordon model, which is really SL2 hat Toda field theory. So yesterday I gave the example of the SLN hat Toda chain. Now that we've moved on to two-dimensional field theories, this is Toda field theory. It's still affiliated to the same affine type of algebra. I take n equals 2 for simplicity. So the sine-Gordon model has got two fields, which are conjugate fields, pi of x and phi of x. So these are canonically conjugate. And I define the lax matrix or the lax connection. So it has these two components, L and M. So L is with some choice of normalization. Okay, this is L, and then M is the same thing with a different sign in these two terms. So I'll just write M is the same thing, but it has a minus sign here and a minus sign here. Okay, so just two sign differences. And the point is that this pair, it defines a connection on in two dimensions, or the zero curvature equation for this pair. If you take if you allow pi and t to depend on time, the equations of motion are equivalent to the following. So pi is dt of phi, and d2 of phi. So d2 t of phi minus d2 x of phi is equal to m squared times the sine of phi. Okay, so this is the sine-Gordon equation. And it comes about from the flatness of this connection. Okay. And I should also write the Hamiltonian. So the Hamiltonian is given by some expression built out of L. So note that the Hamiltonian can be written as follows. So Hamiltonian of sine Gordon, which is the integral over the, I'm taking here the compact case S1. So half the momentum squared plus half the derivative of x, derivative of phi squared plus m squared cosine of phi. So this you can write nicely in terms of the lax components L as the integral over S1 of the residue at z equals infinity of 4 over z trace of L of z squared. And then you have to correct by some term, which is the momentum of the theory, which corresponds to spatial derivative. So integral over S1 of pi dx of phi. Okay. So the key thing I want to emphasize here is that the Hamiltonian is built really out of the lax matrix in terms of some expression which you should remember. It's extracted from the trace of L squared by taking the residue at some point infinity. Okay, so this will become more general in a second when I look at the Godin model. Again, this will be an example of a Godin model. And the Godin model is the most general kind of field theories we can extract from 4D Chern-Simons theory. So I want to give you this simple example, then turn to the slightly more general case of a Godin model. And I think hopefully today I can explain to you why this is an example of a Godin model. And one important thing to see this is that the Hamiltonian has this particular form. It's built out of the lax matrix by some polynomial of the lax. Okay, taking the residue at infinity here. Okay. So let me now describe the Godin model. So it will be very similar to what I told you about yesterday for the finite dimensional Godin model. But everything is generalized because now there's some spatial dependence. So the equations will be similar, but slightly more complicated. So hopefully what you saw yesterday will be useful today in recognizing the expressions I'm going to write. So let's talk about the second example. So this is the second key example, which is the affine-Godin model. And again, the point is that this class of models is essentially the most general class of field theories you can build from 4D Chern-Simons. So let's consider, as before, some set of points. So consider, well, first let me talk about the currents. So a set of capital N, some integer greater than 1. These are G-valued currents. So I call them curly J, subscript I of X. So this is to be compared with yesterday, the finite dimensional case. We had these objects Ji, which were Lie algebra valued. Right. So now we basically are looking at the field theory. So then there's an extra space dependence. These are now functions on the space, whereas before we just had Lie algebra valued objects. So Lie algebra elements. These were parameterizing the phase space of the finite Godin model. Now the phase space of the affine Godin model is described by currents. So this is for I equals 1 to n. And their Poisson brackets are Kac-Moody Poisson brackets. So with Poisson brackets. So here I'm just defining the phase space of the Godin model. So it's similar to the expression we saw yesterday. So Ji of X, but now it's on tensor factor 1. And then J of X, X prime on tensor factor 2. So I should take these at different space-time, different spatial points in general. And then the bracket is equal to the commutator of C12 with Ji1 of x. So this is what we had yesterday if you ignore the x dependence. Now, because there's an x dependence, you get a delta function at x minus x prime. So the currents commute if they're at different points. And crucially, there's an extra term, which is a central extension for this loop algebra. So this is like a loop algebra, but you can, where the loop parameter is the coordinate on the circle, there's a central extension, which is given by some numbers Li, and then C12 times the derivative of the delta function. And here I was taking the current Ji with Jj, and so I get a delta Ij. They commute at different currents commute with each other. So everything apart from the central extension term and the delta is what we saw yesterday. Now we just have this extra spatial dependence and these Dirac delta functions appearing. Okay, so these things Li they're very important. They're called the levels. So these are just complex numbers. They're levels of the currents Ji. Okay, so this is to be compared with the equation I called star yesterday. And because this is another very important equation, it's the affine analog of the constant Kirillov bracket star I talked about yesterday. I'll give this another name, so I'll call this dagger. Okay. So just as we did yesterday, this algebra can be packaged nicely together into Poisson brackets of a Lax matrix. So first, let me define the Lax matrix of the Godin model. What we did yesterday was we took these capital Ji's and we collected them together in a rational function. I'm going to do the same with these currents. I just collect them into a rational function, and that will define the Godin Lax matrix, which is not quite related to the capital L of the zero curvature equation yet. It's just some auxiliary Lax matrix, which is more fundamental in some sense. So what I do is, as in the finite Godin model, I pick any distinct points. There are some zi's in the complex plane, and I define the Godin Lax matrix, really affine Godin Lax matrix. And also I can define another object. So because I have currents, I can collect them into a rational function. And I also have these numbers, Li, which I can collect into a rational function. And so this defines a crucial object that appears in the 4D Chern-Simons action. So this is the twist function. So the Godin Lax matrix is the collection of all the currents. So I call it capital gamma, because it's not really L, it's going to be related to L. So it's just a combination of all the currents at the different sites. So it's Ji of x over z minus zi. And the other thing I define is the so-called twist function, which collects together all the levels. So sum over I equals 1 to n. Li over z minus zi. Okay. And I can, for simplicity, it's useful to add a constant term here. So I choose an L infinity not 0. So for some L infinity non-zero, the reason I add this is because this will allow phi to have as many zeros in the finite plane as poles. So if I don't put this term, then there's going to be a 0 at infinity. So this is just for convenience to bring all the zeros to the finite plane. And it's not strictly essential. So you can also ignore this term. So I just build these two objects. And then the point is that this dagger relation, the fundamental relation for the phase space of the Godin model, can be rewritten as a Lax algebra. So this dagger relation the fundamental Poisson brackets of the Godin currents. This is equivalent to the lax algebra. So if I take the Poisson brackets of two Godin lax matrices, so at different spatial points and different spectral parameters, so gamma of xz with gamma of x prime z prime, and I put them in different tensor factors 1 and 2, this is equal to, this is very similar to what we had yesterday. So there's this classical R matrix, Casimir over z prime minus z, and then the sum of the two lax matrices. So this would be the same as yesterday, but now because there's some spatial dependence, I also have a Dirac delta function, which comes from this Dirac delta function. And then the levels combine together into the R matrix times the difference of the twist functions at the different spectral parameters z and z prime. Okay. So again, this is all the same as yesterday. There's just some extra spatial dependence, and the levels enter through this central extension term, and I have this delta for the spatial dependence of the Godin lax matrices. Okay. So here, this algebra is plays an important role in the description of these classical field theories. And there's an important classification here, which is there are two different types of models. The first one is where phi is constant, so that the central extension term disappears. These are called ultralocal, and they're somewhat nicer because they're easier to quantize. It's very well understood how to deal with them. Whereas the case when phi is not constant is the interesting case where we don't really know much about the quantization. And these will be the kind of theories you typically build with Chern-Simons. So just some terminology. If phi is constant, then the Godin model is called ultralocal. This is the case called ultralocal. And in the language of 4D Chern-Simons, these will be essentially associated to what are called order defects. So what's nice is that everything that is familiar from Lax and Godin model perspective has a translation, right, an equivalent description in the 4D Chern-Simons story. And the other case, which is phi of z is non-constant. So therefore, the central extension term is present. So this is called non-ultralocal. And these will correspond to what are called disorder defects. So this is the case I'll focus on in the Chern-Simons story. So disorder defects. Okay. So given this lax algebra, I haven't told you the dynamics yet. So this is just the phase space. It's repackaged nicely in terms of this lax connection. But now the Hamiltonians, which describe the dynamics on this phase space, they're associated, or the local Hamiltonians are associated to the zeros of the twist function. So we can associate to each zero, so call them zeta I of the twist function. So the zeros will play a crucial role as well in the Chern-Simons story. so these zeros, so points where phi vanishes. So this is for I equals 1 to n. So to each of these zeros, we associate a quadratic Godin-Hamiltonian. Quadratic affine Godin-Hamiltonian. So what you do is essentially what we saw for the Toda case. So these Hamiltonians are labeled Qi. So they're given by some residue at the zero, at zeta I, of dz over 2 phi of z. You integrate over the circle, so there's some x dependence, which you integrate over. And then what you integrate is the trace of the Godin-Lax matrix squared. Let me write it like this. So for general Lie algebra, you have a bilinear pairing angle bracket. And so you can plug in the Lax matrix twice. So this is a quadratic object in the Lax matrix, which in the SLN or matrix Lie algebra case is just trace of the Godin-Lax matrix squared. Okay, so this is reminiscent of the expression that we had in the Toda case. I'll explain why in a second. So this defines a flow. So these Hamiltonians, they are functions on the phase space, and they define a flow, time evolution on this phase space. So we can let d by dt I, some time evolution, be given by Poisson brackets with this Hamiltonian. Okay. Okay, and now the claim is that all of this put together produces some Lax equations. So I have a time evolution on a phase space with some fields which are these abstract currents. But using this Poisson bracket, if I can use this Poisson bracket to compute the Poisson bracket with Qi of the Lax matrix itself, and so I get the time evolution of the Lax matrix, and I can rewrite this as a zero curvature equation. So the point is that the Godin model has associated with it some Hamiltonians, and these Hamiltonians have described flows on the phase space which are of the zero curvature form. So it's describing some integrable field theory. So define these matrix Mi of x and z. So it's 1 over phi prime of zeta I. So here I'm assuming that zeta I is a simple zero. Of phi. But the derivative doesn't vanish. And if not, then there's a more general formula, but it's not relevant here. So the simplest case is a simple zero, and then you have this expression. So you define this Mi, and I define a straight L, which is going to be the Lax matrix of the zero curvature equation, as 1 over the twist function times the Godin-Lax matrix. Okay. So the claim is that these two things you can check satisfy zero curvature equation. So if you define these, then the dynamics of the Lax matrix capital L is exactly a zero curvature equation. So d by dti of the Lax L minus dx of capital Mi this is just the commutator of Mi with L. Let me put plus. Okay. So in other words, the Godin model is some machinery for generating integrable field theories because you get zero curvature equations with spectral parameter dependent lax matrices. Okay. So these JIs, the current JIs, are abstract currents, but the point is that in general, a field theory will depend on some particular fields like phi or pi, and you say that it is a Godin model if you can bring the model to a form which is of this particular form. So if you can write these Godin currents in terms of the fields of the theory itself. So in general, affine Godin models describe 2D lax integrable field theories whose phase space is described by Poisson commuting Kac-Moody currents. So by this relation dagger. So if you have a given field theory and you can bring its field, you can use its fields to build some currents that satisfy this relation dagger, then you're dealing with an affine Godin model. Okay. So it's the same thing as in the finite dimensional case yesterday. We had a particular setup where we had coadjoint orbits, and the JIs were HI, lambda I, HI inverse. So in the finite dimensional case, we were dealing with a model which had particular field content, HI, or dynamical variables, HI, and this particular combination satisfied the crucial relations star of the Godin model. So that means that the model we were looking at was a Godin model. In the same way in the field theory, if your lax integrable field theory has fields which you can combine to build Kac-Moody currents satisfying the dagger relation, then you're dealing with an affine Godin model. Okay. So let me show you why, for example, the sine-Gordon model is a Godin model. So this is what I didn't have time to describe yesterday in the Toda chain case. So the Toda chain I claimed was an example of a Godin model, finite Godin model. Now the same thing is true for the sine-Gordon model, which is an affine Toda theory. You can write it, you can rewrite it as a Godin model. So remark, the sine-Gordon model it's a realization of what's called, so it's a slightly more general Godin model, so it's called Z2 cyclotomic. So SL2 hat Godin model, so it's an affine Godin model. And it has another slightly more general feature than the one we talked about just above, which is that it has irregular singularities. So what I mean by this, by cyclotomic, Z2 cyclotomic and irregular singularities, to tell you that, I just need to write for you the lax matrix. So the lax matrix of the Toda theory is a Godin lax matrix of the following form. So it has poles at the origin, and a double pole at the origin, right? So this is just two currents which are sitting over the simple pole and double pole, and plus some constant term which represents a pole at infinity, and the twist function is 1 over z. Okay, so this is to be compared with the expressions we had before, the sum of ji over z minus zi. So that was only simple poles. Now we have this double pole term. And I didn't have any constant term. There was no plus constant. This is coming from a double pole at infinity as well. So these are two new terms which correspond to the fact that you have irregular singularities. And Z2 cyclotomic is saying that these currents are actually, this one is Cartan valued and this one is off diagonal valued. So these are not quite general matrix valued currents. This one has to be Cartan and this one has to be off diagonal. So specifically, I need to tell you how these are related to the fields of the Toda model, of the Sine-Gordon model. So this is the Godin-Lax matrix with the currents given as follows. So J0, 0 is I over 4 pi times pi plus dx phi times Cartan. So it's a Cartan valued matrix with these fields along the diagonal. And J01 is off diagonal. So it's e to the minus I phi times the matrix, the Lie algebra element E, plus e to the I phi times the Lie algebra element F. And this one is also off diagonal. So J infinity is constant. And it's just given by E plus F. Okay. So all I'm saying here is that if you run the arguments I just presented, so you build the matrix capital L here by taking this whole thing, gamma, dividing it by phi, you get exactly the Lax matrix I wrote before for the Sine-Gordon model, but using these expressions for the currents. And the M you can also build from this expression by a similar procedure. Okay. So any question? Okay, so hopefully this was paralleling the story from yesterday. So I showed you how to build field theories which have zero curvature equation for their equations of motion from a Godin model. And the crucial thing to remember is that the ingredients were some Kac-Moody currents and some which built Lie algebra valued Lax connection. And crucially, there was also this twist function phi. So these are the two ingredients that will enter into the 4D Chern-Simons story. So now what I want to do is explain how all of this setup emerges very naturally from a gauge theory in 4 dimensions. So the idea, as usual, is to take the 2 dimensions we're working with, increase them by 2 real dimensions or 1 complex dimension. So we're working in 4 dimensions. Write down the gauge theory in 4 dimensions that will produce all of this Lax story. Okay, in particular gauge. So let me discuss the specifics. So this you've already seen from Yamazaki-san's talk. But I want to describe it again, perhaps in more detail. And related to this Godin story. Okay, so as before, what I'll just do is write down the action. So you've seen the action. So to write down the action, I need to fix a meromorphic 1 form. In fact, Masahito actually talked about a particular case where the omega is not meromorphic. I'll stick to meromorphic cases. That's what corresponds to Godin models. I'm not sure about what the non-meromorphic case, well, the case with branch points corresponds to. So let's just take a meromorphic one-form omega on CP1. And to match the story I was telling you about in the Godin model, I'll take omega to be able to form this twist function times dz. Okay, so this is where the twist function comes in. It's literally just the omega in the 4D Chern-Simons theory. So it's the sum of Li's. I'll take this example where you have the sum of the Li's over Z minus Zi that we looked at just a second ago, and then minus this L infinity. Okay. So this is the one form omega. And as I said, it has n zeros in the finite plane because I've taken L infinity to be non-zero. So with zeros, zeta I, or like I'll call these zeta underlined. So this is the collection of zeros. So this is the set of zeros of omega, and it has a set of poles and poles. So I call Z underline the set of finite poles. So it's Zi from I equals 1 to n. So there's also a pole at infinity. But that won't play such an important role in this talk. Okay. And if I remove the L infinity, there's a double pole at infinity. Sorry, there's a double pole at infinity with L infinity, non-zero. And it's a simple pole if I remove L infinity. Okay, so this is just a part of the data of the Chern-Simons action. So now you can write down the Chern-Simons action. So consider the action S for D Chern-Simons, which depends on a single gauge field. I have a different normalization to what Masahito had. So I over 4 pi. This is just to match notations in the Chern-Simons in the Godin story for the Poisson structure. So you integrate over the whole 4 dimensions, which is a 2-dimensional surface with coordinates x and t, and the spectral plane CP1. So omega wedge Chern-Simons of A. The Chern-Simons is just A dA plus a third A with A. Okay, so and then I take so you can think of 2 examples. Sigma is R2, or as usual, you can take it to be the cylinder if the spatial direction is compact. And A here is a field which has 3 components. So as Masahito already emphasized, there's no dz component because we're wedging with omega, which already has the dz component. So we just need 3 components for A, the x, t, and dz bar component. So so this action is for a smooth G-valued field. So A, which has component A dt plus AX dx plus AZ bar dz bar. And so for reasons I'll explain in a second, we want later to allow A to have certain singularities. So I'll remove from the space-time, I remove the zeros of omega because omega vanishes there, so I'll be allowed to let A have poles there. I'll be allowed to have A be singular at those points. So initially, I just say it's a smooth valued field on the surface sigma cross CP1, but minus the zeros. I can remove the zeros because I'll be allowed to make A singular there. So it shouldn't be smooth at those points. It should be allowed to have singularities. Those singularities will be compensated by the zeros of omega. So everything will be fine. Okay. So first remark is you might also worry about the singularities of omega. Omega itself has singularities. So this is where it starts to get more subtle than the 3dBF story. Now we have to worry about this action because there are singularities in omega and we can potentially allow singularities in A, which will be very important. And so this is something we didn't have in the 3dBF case. So omega is singular. It's singular along the surface defects. Which are at sigma cross the points Z where omega has poles. Okay, so you have, let's say, R2 cross CP1. So because omega has poles at certain points on CP1, Z1 to Zn, the action is potentially singular along these surface defects, which span all of R2 and are located at certain points on CP1, at those points Zi. Okay. So nevertheless, it turns out that if you only allow simple poles, which is what I'm doing here, if you allow only simple poles, the action is actually well defined. There's no problem. So nevertheless, so omega wedge Chern-Simons of A is locally integrable near these surface defects. So in other words, the action doesn't blow up there, so it's fine. And the way to see this is just if you think about pulling out a dz bar component from Chern-Simons. So if you just look at omega wedge dz bar, so this dz bar comes from Chern-Simons of A. It has a dz bar component. So let's think about this expression. This expression is locally around Zi. It looks like Li over Z minus Zi plus something finite times dz wedge dz bar. But then dz wedge dz bar, if I convert to polar coordinates centered around the point Zi, so I can write this as so in polar coordinates with Z is equal to Zi plus R e to the I theta, then this dz wedge dz bar is just minus 2I R dr wedge d theta. And this denominator here is R e to the I theta. So the R on the denominator cancels with the R in the measure, and so everything is fine. It's bounded. And so it looks locally like minus 2I L1, Li, plus something of order R, or there's an e to the minus I theta, dr wedge d theta. Okay, so you can integrate this locally around these yellow defects, the pole where the poles live. If there are higher order poles, then you need to modify the action a bit to regularize it, but there's a well-defined procedure for doing that. So here we don't need to worry about this because all the poles are simple. Okay, so that was one first thing that is different from 3dBF. You have to worry about singularities in the action. So another thing is that because omega vanishes at the zeta i's, you can, in principle, and you should, allow A to be singular there. Because then the action is well defined the singularities at A will be compensated by the zeros of omega. So we can and we should allow this. This will be crucial to get meromorphic lax connections. So the second remark, which is again in contrast with the two-dimensional case, or with the one-dimensional case, is that if you have zeros, so if the set of zeros is not empty, so that's the crucial case, which I said was non-ultralocal. If phi is non-zero, so it's non-constant because, for example, it has zeros, then when omega has zeros, you should allow A to be singular there. You can and should allow A to be singular there. So by there, I mean along these defects at the zeros. Okay. So these are not really defects. Defects are the ones with the at the poles. These I don't tend to call these defects. So we can allow the A to be singular at these zeros. So namely, what we'll do is we'll define the space of fields. So we define the space of fields of the 4D Chern-Simons theory. So we work with one forms. So one forms A, so that one forms on sigma cross CP1 without the zeros, valued in G, for which the various components are allowed to have singularities as follows. So for which AZ should be smooth. Okay. So I'll list the things which are required to be smooth. Omega wedge A should be smooth. And also omega wedge the curvature of A should be smooth. So these should all extend to smooth functions, extend smoothly to sigma cross the whole CP1. So whereas A is allowed to have singularities, you want that when you wedge it with omega, the singularities are removable. So the singularities of A should be simple poles, or singularities which will become simple poles when A becomes meromorphic. But the singularity should not be stronger than the zeros of omega, so that when you wedge omega with A, you can smoothly extend this wedge product to all of CP1. And then another technical requirement is that the curvature of A should also extend smoothly. So it shouldn't have any stronger poles than A itself. Okay, no stronger singularities. So in particular, the curvature has a term which is dA. So that will have the same kind of singularities in the Z direction. But then there's potentially a term which has stronger singularities because you take A wedge A, and you want that term to not have any stronger singularities. So this is a technical requirement. And this defines the space of fields for which 4D Chern-Simons will become exactly an integrable field theory. So this is something important to bear in mind, is that we restrict the set of fields of this 4D Chern-Simons theory to have a certain set of singularities at the zeros of omega. Okay, and also I don't want singularities in AZ, because AZ I want to set it to 0 very soon, and so I don't want it to be singular. I want it to be smooth everywhere so that I can set it to 0. Okay. Okay, so now we have an action with defined for some set of fields which have certain allowed singularities at the zeros of omega. And the singularities of omega itself are not problematic. So we have a well-defined gauge theory, or a well-defined action, and now the question is it a gauge theory? So we can test for gauge invariance. Okay, so let's look at the variation of the action under some smooth function of the space-time coordinates and zz bar. So I can look at the action at the gauge transformed field. So this, remember, is GA G inverse minus DG G inverse. So I evaluate the action at the gauge transformed field. And if you do the quick algebra, it's just the original action at the untransformed field. But then there are two correction terms. So I over 4 pi integral of sigma over sigma cross CP1 of omega wedge d G inverse dg paired with A, and then plus I over 4 pi integral of sigma CP1 omega wedge 1/6 of G inverse dg paired with G inverse dg commutated with G inverse dg. Okay. So it's not gauge invariant, clearly, unless we can show these two terms vanish. But the problem is that these don't quite vanish. What you can do is that instead of writing them just as integrals over all of space-time, all this four-dimensional manifold, you can show that they localize exactly at the poles of omega. So they localize exactly at the defects, which are the poles of omega. So the claim is that although this action is not gauge invariant, the failure of gauge invariance, which is these two terms, localizes at the poles of omega. So it fails to be gauge invariant only at the poles of omega. And the idea will be to impose boundary conditions on the gauge field A and the gauge transformation parameter to kill those variations, so to make it gauge invariant. But so initially there's a failure of gauge invariance exactly at the poles of omega. So the claim is that both integrals localize at the poles of omega. Okay, so this I'll localize. I'll not show explicitly, but I'll write the precise way to localize these integrals. So both of these integrals localize at the poles of omega. So the action is gauge invariant away from these poles, but the gauge invariance is broken at those poles. So we can say that the gauge invariance, which we were expecting to have, is broken at the poles of omega, or at the defects. Which are sigma cross the poles of omega. Okay, so this is again different to the 3dBF story where the action was gauge invariant. Now the action is not quite gauge invariant, and we need to do a bit more work to make it gauge invariant. So we need to kill this boundary variation, or this variation localized at the poles of omega. So I'll just introduce a bit of notation to write this in a more local way. So right now it's written as an integral over all of sigma cross CP1. I want to show you that it's actually some integral localized only over the poles of omega. Okay. So it requires us introducing some notation to rewrite this in a simple way. So introduce what's called the defect Lie group. So this is a group which is labeled by the poles. And it's just in this case that I'm looking at with simple poles, it's just the product of n copies of the group G. Okay, so we have the surface sigma with the poles on CP1. And at those poles, Z1 up to Zn, at each of those poles, I assign a copy of the group G. So this defect group is just a collection of copies of G for every point on the defect, for every pole of omega. And also the corresponding Lie algebra is the defect Lie algebra. So this is just a collection of all the Lie algebras at every point. Okay. So it's like a group that's sort of assigned to the defects. And so this Lie algebra, the defect Lie algebra, is it's endowed with a non-degenerate pairing. So which is denoted like this, double angle bracket subscript omega, because it depends on the meromorphic one form omega. So it's a pairing, so between GZ, the defect Lie algebra, and itself, and it maps into C. So the way it's defined is just the pairing between a defect Lie algebra element, which is just a collection of Lie algebra elements for each site. So the pairing between such an element and another element, yj for j equals 1 to n. So another collection of Lie algebra elements for each site. Their pairing is just the sum over all the sites of Li xi paired with yi. So you pair the Lie algebra elements at each site together, and then you sum them weighted by the levels. Okay. So this is just some notation to be able to rewrite this variation in a way that's manifestly localized at the poles of omega. Okay. So so let me write the action. So with this notation, first let me also say that so we have these defects, okay? And so if you have so these defects, they sit inside. So this is the defect. So sigma cross all the poles. This sits inside the total space. And so if you have a field on the total space, you can pull it back or restrict it to the defects. So this is an embedding. So if I take, say, for example, the Lie algebra valued one form, which is a one form on this total space valued in G, I can restrict it to the defect. I can pull it back to the defect. So for one from omega, we have its restriction to the defect. So its restriction to the defect is given by one form that's living on the defects. Okay, I just restrict it, so rather than being on one form on the whole space, it's just living on the defect. But a one form on the defect, what is it? It's just a one form for each of the copies, for each of the poles. So there's a one form associated to Z1, a one form associated to Z2, and so on down to Zn. So really, this is just the same thing as a one form on sigma, which is valued in the defect Lie algebra. So if I restrict a one form on the total space to the defects, that's the same thing as giving a single one form on the surface sigma that's valued in the defect Lie algebra. Okay. And similarly, for the group valued function on the total space, sigma cross CP1, I have that its pullback to the defect is just a function on the surface sigma, on the space-time sigma, valued in the defect Lie group. Okay. So now I can write down the gauge variation in a nicer form. So now we can write the equation I had before. So the gauge variation of the 4D Chern-Simons action, it's the 4D Chern-Simons action for the original field plus two terms. The first one is an integral only over sigma of pullback, so G restricted to the surface defect dG, and then paired with the restriction to the defect of A. Okay, so what's going on here is just I take the G inverse dG paired with A, but I restrict both these two Lie algebra valued fields, G inverse dG and A, I restrict them to the defect. And then because these are defect Lie algebra valued functions, I can pair them under the defect Lie algebra pairing, and I can integrate them over sigma. So this is really just an integral over the defect, because it's purely an integral over sigma. There's no integral over CP1 happening. That's purely on CP1 is purely being localized at the defects. So this is really to be thought of as an integral over the defect only. And then similarly, the WZW type term, it's an integral that's localized in a tiny tubular neighborhood of the surface defect. So I is some interval, which is as small as you want, because the WZW term is three-dimensional, so I need to extend the field G to some tubular neighborhood. And then the second term in the variation is just this WZW type term. Okay, but again, the point is you should think of this as being localized on a tiny little neighborhood of all the defects. Okay, so what this shows is just that the action is gauge invariant if you look at it away from the defects, but on the defects, the gauge invariance is broken. Okay. But we can restore gauge invariance by trying to get these two terms to vanish. And so this is what this is where we require imposing boundary conditions on the gauge field. If we impose boundary conditions such that these two gauge variation terms vanish, and why is it boundary conditions? Because these variation terms, they involve the restriction of the gauge fields to the defect. So if we choose suitable restrictions, if we say that when you restrict the gauge field to the defects, it takes values in certain subalgebras or subspaces, then you will be able to make these terms vanish. So we want to impose boundary conditions so that this kind of pairing actually vanishes and the variation is therefore 0. Okay, so for that, we introduce some further notation. So let's call K. We choose a subalgebra of the defect Lie algebra. So let this be an isotropic Lie subalgebra. So isotropic just means that if you take the pairing under this omega pairing between two defect Lie algebra elements in K, this should be 0. So this should be 0 for all x and y in K. It's a subalgebra on which the bilinear pairing vanishes. And we also denote the corresponding group by capital K. So that this be corresponding subgroup of GZ. So I want to impose boundary conditions that, so let's say I want to make this vanish. So I can do that by saying, if I restrict the gauge field A to the defect, it should live in K. And if I restrict the group valued element G to the defect, this combination should live in K as well. If that's the case, both these guys will be in K, and so the pairing will vanish. So we can impose, or we can make the two above integrals vanish if we impose that when you restrict the gauge field to the defect. So what should it be in general? In general, it will be something valued in the defect Lie algebra. But I want it to actually be valued in the isotropic subalgebra. So so that means that when you restrict it to the boundary, it's really valued in K, not in the full defect Lie algebra. And also, you require the same thing of the group valued element G, the gauge transformations. So you want that if you restrict the gauge transformations to the boundary, so to the defect, then you get functions valued in the group K. So rather than being valued in the full defect Lie group, they will be valued in K. So this would be a subalgebra of the functions valued in the defect Lie group. Okay, so these are just boundary conditions. We're saying the gauge field, when restricted to the defect, should really live in this subalgebra. And the corresponding gauge transformation parameter also lives in the subgroup. And if that's the case, then this pairing here clearly vanishes, because G inverse DG restricts to something in the Lie algebra K, and A restricts to something in the Lie algebra K, but then they pair to 0 under the pairing because K is isotropic. So this would this would restore gauge invariance. So
excuse me.
yeah.
Could you explain some explicit form of that explicit examples
Specific
of
examples of this?
Yeah.
So I mean there. So a simple example is if you take GZ to be 2. So if Z has 2 points, so if Z consists of just 2 points, so Z1 and Z2, then what is GZ? GZ is G plus G. It's just 2 copies of G, right? There's two defects, so there's 2 Lie algebras. And an isotropic subalgebra. So then I have to tell you what the pairing is. So the pairing, I think I want to take so x1, x2 with y1, y2 will be some L1 pairing of x1 with y1 plus L2 pairing of x2 with y2. Okay, that's the formula I used before. Now, if the levels are, if these are the only 2 poles, then there's two simple poles, so the residues should be opposite. So these are really opposite levels. So this will be minus L1, if that's the only two poles. And then you can choose subalgebra. I think the diagonal subalgebra should work. So if x1, y1 are the same, and x2, y2 are the same, then this vanishes. So this is equal to 0 if x1 equals x2 and y1 equals y2. Okay, so then this is called the diagonal subalgebra. It's the subalgebra of pairs x in G plus G. Okay, so this is one example. It's the simplest one. There are more interesting examples. Okay, so you can impose boundary conditions to kill these two terms. And then once you impose boundary conditions, so now we're looking at a theory where the gauge field A has certain poles at the zeros of omega, and it has boundary conditions at the poles of omega. Okay, so these are boundary conditions. And I think I don't have time to explain an interesting way, a nice way to impose these boundary conditions, which is usually in a gauge theory, saying that a gauge field is equal to something. So you're saying the gauge field is living in this subalgebra. What you should really say is that it's living in the subalgebra up to a gauge transformation. So you don't really equate gauge fields in a gauge theory. You should equate them up to a gauge transformation. So there should be some gauge transformation which witnesses these boundary conditions. And this is where the notion of edge modes come in, but I can't really introduce these. So really what you want to introduce is a set of fields. So the nicer way to impose these boundary conditions, and the reason it's nice is because you see, if I impose these conditions, I'm restricting the allowed gauge transformations. I'm saying I don't want all gauge transformations possible. I'm only allowing gauge transformations which also satisfy some boundary condition. And a nicer way to do this is to say, let's not restrict the set of gauge transformations. And to do that, you have to allow the gauge fields to satisfy the boundary condition only up to some edge mode. So the nice way to impose these boundary conditions is to do the following: to couple the gauge theory, or couple the bulk theory, or couple the gauge field A to what are called edge modes. So an edge mode is a field that's living on the surface sigma. It's a field living on the defect. It's a field living on sigma valued in the defect Lie algebra. And the new action is just the old action. So there's an action that depends on A and H now. It's just the 4D Chern-Simons action. But then I add two terms which will cancel the gauge variation we had before. So I add terms which look very similar to what we had above, but with the edge mode H instead of G. So I add to the action this term. So I couple the gauge field to this term which lives on the defect. So in other words, I'm modifying the bulk action by a defect term. And the point is that what this does is if you let H transform suitably, it will cancel the bad gauge variation of the bulk action, and you're going to get a gauge invariant action. So I'm just adding these two terms to the bulk action, and now the claim is that if I let H transform, if we let H transform as follows, as multiplication on the left by G, then this action is actually gauge invariant. Okay, so we started with an action that was not quite gauge invariant because when you vary it, you get some terms. These terms are localized on the defects. What you can do is you can introduce some fields on the defects with this term in the action to couple them to the gauge field. And you let these fields called edge modes transform in this way, which is reminiscent of what we had in the 3dBF case. And then this combination, this whole action actually is gauge invariant. So the bad terms which come from the variation of this bulk piece cancel exactly with the terms coming from this boundary, or from these defect terms. Okay. So this is a nice way of getting a gauge invariant theory. So in the 5 minutes I have left, I want to tell you how, now that we have a gauge theory, so the point is now this is an honest gauge theory, which is invariant under all gauge transformations. And the thing I need to tell you as well is that the edge mode, remember I told you the edge mode, what it does is it witnesses the boundary condition. So there is a crucial relation. There is a crucial condition relating the edge mode and the gauge field, which is the following, is that if I take the gauge field restricted to the defect and I transform it by the edge mode, this will be in the defect Lie algebra, in the isotropic subalgebra. So this is really the boundary condition, but now it's imposed up to a gauge transformation by the edge mode. So we have the crucial, I should say, boundary condition. Okay, so we still have a boundary condition, but it's imposed up to this edge mode. The edge mode sort of is what witnesses the boundary condition on the gauge field. The gauge field is not literally satisfying the boundary condition, it's satisfying them up to this gauge transformation by the edge mode. Okay, so this is the setup. We have this gauge invariant action where these two fields A and H are not quite independent, they're related by this boundary condition. Okay, so bulk action, not quite gauge invariant, we add these two terms to make it gauge invariant. And now we just apply a similar reasoning, I can do it very quickly, similar reasoning to the 3dBF case to produce 2D integrable field theories. So we have a gauge theory, and we want to show that upon gauge fixing to some particular gauge, we produce integrable field theories with lax connections as equations of motion. So this is my starting point, and now let me explain the 3 steps to produce a gauge theory, an integrable field theory. So, very last section for this lecture. So we want to go from 4D Chern-Simons to a 2D integrable field theory. So here's the rough idea and the key idea. So we have a gauge field which we want to turn into, so we want to turn the smooth 4D Chern-Simons gauge field so remember this gauge field is A equals AX TX Z. Let me write ZZ bar to emphasize that it depends smoothly on Z, plus AT of TX ZZ bar dt plus AZ bar of TX ZZ bar dz bar. So that's the gauge field. So we want to turn this into a meromorphic (2D) integrable field theory lax connection. So what's a lax connection? It's this thing I called curly L of Z, which has 2 components, L of Tx and Z dx plus M of Tx Z dt. So here I've written only z dependence because these are meromorphic functions. So the first crucial difference between these two things, if we want the gauge field to become a lax connection, like before we had the BZ field becoming a lax connection and AT becoming the matrix M, we need to get rid of the AZ components, and we do exactly as we did before. So we need to get rid of this term. So we need to kill off this term. So this will be step one. The second thing is that we want to turn a smooth field into one which is meromorphic. And so that's a step two. And then the last thing is, this is just a connection. It has no relation to H. H is like a field living on the defect. It will be the field of the integrable field theory. But the connection A as it stands has nothing to do with the gauge, the field H. So the last thing to do is to solve the boundary condition. So we want a lax connection that is related to the edge modes. Yeah, realized, sorry, that's realized, let me say. In terms of the edge modes. So this edge mode is just going to be the field content of the integrable field theory. So the lax matrix should always be expressed in terms of those fields. So we want to realize the lax matrix in terms of the edge modes. So that's the third thing we want to do, to realize it in terms of the edge modes. So those are the three steps. And the three steps are easily achieved. First thing, because we have a gauge theory, we move to the gauge AZ bar equal to 0. Okay, so let me write here this three steps. So step one, move to the gauge AZ bar equal to 0. So that gets rid of the last component, so we have something that's more like a 2D connection. Okay. So I'm not giving you the details, I'm out of time. So then if you write out the bulk equations for this in this gauge, so the bulk equations, meaning the equations for the field A, they read del bar of A is equal to 0, which I can call L now, because I got rid of the Z bar component, so A and L are of the same form. This is really L. So del bar of A is equal to 0. And we just solve this equation. So solve this equation. And if you remember, we imposed some restrictions on the singular structure of the field A. We said it has poles which are not stronger than the zeros of omega. So therefore, the solutions will be some meromorphic function with poles at the zeros of omega. So that just says the solutions are the form L is some meromorphic function. Some meromorphic expression. In Z. So that deals with the second thing. We want it to be meromorphic. And once we've solved the bulk equations, we're only left with the, essentially, we solve the equations of motion for A. This will essentially disappear on shell. So then we get just an action which is two-dimensional. So we're really now dealing with a two-dimensional theory. So the last step is just to solve the boundary conditions, this blue thing. And once you solve the boundary conditions, you're solving for the lax connection in terms of the edge mode. So this is just the step 3. So of course, to do all of this in detail, it takes a lot of work, but I'm just giving you the procedure. I'm outlining the procedure to get from the 4D transassignments to the 3D theory, to the 2D theory. So the step 3 is just solve the boundary condition. which was that H inverse gauge transformation of IL should live in the defect Lie algebra, sorry, in the isotropic subalgebra. So solve it for L in terms of H. So what we get in the end is L. We get that L is expressed in terms of H. Okay. So at the end of the day, what you end up with is a flat connection that's meromorphic in Z that depends on the fields living on a two-dimensional surface. So there's some two-dimensional field. And moreover, the equations of motion for the action that we derived. So this satisfies the flatness equation, or this satisfies the zero curvature equation. So we get a two-dimensional integrable field theory out of this. Okay, so just to quickly summarize, we can also derive the Poisson structure for the 4D Chern-Simons theory, and it turns out it gives you exactly the Lax algebra for the Godin-Lax matrix that I told you about before, in a similar way to the three-dimensional case. In this four-dimensional story, people have studied in a lot more detail the kind of a very general class of boundary conditions. So there's a lot of examples of boundary conditions, a very large class of boundary conditions you can impose to produce different integrable field theories. One thing that's less understood is how to go to high genus. The only examples we've really discussed in great detail in the literature are the Riemann sphere and the elliptic curve. High genus is still fairly open, and it would be interesting to construct models in this case. Okay. Sorry for overrunning. Thanks.
Thank you very much.
Okay, so today I want to talk about three-dimensional integrable field theory. So I need to first address the question of what I mean by this. And the answer is it's not completely clear, because the notion of lax integrability, which I've been using throughout these lectures, is not fully established, or it's not agreed on what is the right lax formulation for integrable field theories, whatever they are, in 3 dimensions. So the first section is more of a question, which is lax formulation with a question mark. So if we want to describe these so-called 3-dimensional integrable field theories using a gauge theory, like I did for 1- and 2-dimensional field theories, we need to understand what's the appropriate notion of lax formulation. So recall that in 1D, so in 0 plus 1D, we had 3D mixed BF theory, which gave rise to the lax equation. So dtL is equal to m commutator with L. In 1 plus 1D, the accepted or very general formalism that works for many integrable field theories is 4-dimensional, which comes from 4-dimensional Chern-Simons. And that formalism is the formalism of flat lax connections. So lax connections which satisfy the zero curvature equation. In particular, there's a natural way to go from lax equations to lax connections by adding this extra term, which is there now because things depend on space. So then the obvious question is, if you go to 2 plus 1 dimensions, what should we use as a natural lax framework? So the first question is, what's the correct lax formulation? So what is an appropriate lax formulation? So I should say everything today will be more speculative. There's no definite answer, but I'm going to make some proposals and try to connect it with what's known. So let me start by giving some examples. of known integrable field theories in 3 dimensions which have some form of lax formulation. So the first very famous one is the KP equation, and the lax formulation is using what's called pseudo-differential operators. So let's take the example of KP. So Bedonsev, Bedviashvili. Equation, which is some one-dimensional higher version of KdV. So it's d by dx of the KdV equation, which in some convention is 4 dtu minus 6u dxu minus dx cubed u, and then equals, and then there is some sign convention, 2 different versions, plus and minus. I'll take plus, for example, and then dy squared of u. So u is now a function that depends on 3 variables, x, y, and t. And this is the equation governing the KP. It's the KP equation. Okay, and so the point is that this can be written in the following form. So it has a lax formulation. Can be written somewhat surprisingly initially as a zero curvature equation. Namely, dt of some L minus dy of some M is equal to M commutator with L. Where, so this is more the lax equation for a 2-dimensional field theory, but the point is here L and M are themselves differential operators. So the 3rd dimension comes in a very awkward way through the fact that L and M are themselves differential operators. So where L and M are given by L is dx squared plus u, and M is dx cubed plus 3/2 u dx plus 3/4 dx of u plus 1/4w. So w is some other field that depends on all coordinates. Okay, and so the point is there is a 3rd dimension which enters through the fact that L and M are themselves differential operators. So it's really a 3-dimensional differential equation. Now there is no longer any spectral parameter, so no auxiliary complex parameter. And if you write out what this equation, this zero curvature equation says in terms of these explicit L and M, so this equation is equivalent to dx of w is equal to 3 dy of u and 4 dt u minus 6 u dxu minus dx cubed of u is equal to dy of w. Okay. So it's a pair of equations for u and v, u and w, but you can eliminate w very easily and you get back the KdV equation. Okay, and once you know u, w is fixed up to a constant. Okay, so that's the KP equation, and it has mysteriously a zero curvature form, but that's because the operators L and M themselves are not matrices which are meromorphic in some parameter. They are themselves differential operators. And there's a corresponding version of KP. So the reason why this sort of works is because you see, if you set things to be independent of y, then this equation becomes the KdV equation. Okay, and in the lax formulation, if you set things independent of y, this term disappears. And in fact, KdV is a field theory. It's 1 plus 1 dimensional, but it has a lax formulation, a lax equation. So this is so note that KdV, which is 1 plus 1 dimensional, just by taking things to be independent of y in this framework, has formulation as a lax equation. So even though it's a field theory, it has a lax formulation, but now again, where L and M are themselves differential operators. So the lax formulation is dTL is equal to M commutated with L, where L and M are basically these formulae, but you ignore W. So L is dx squared plus U, and M is the same formula, but without the W piece. Okay. So this is just to say that this formulation of a two-dimensional field theory is slightly unconventional. And in the same way, this formulation of a three-dimensional integrable field theory, although very standard, it's a bit unconventional because there's no spectral parameters, so we can't hope to play the same game as we did in these other settings where we had an extra Riemann surface where the spectral parameter lived. We can't hope to do the same thing here. Okay, so that's a lax formulation which maybe doesn't have any gauge theoretic origin. So an alternative to the lax formulation in 3 dimensions is coming from anti-Self-Geo Yang-Mills. And we saw this in Masahito's talk, where if you reduce down by 1 dimension, you get the Bogomolny equation. So the second possible framework for lax formulation of 3D integrable field theories is the Bogomolny equation. So it's a 1D reduction of anti-Self-Geo Yang-Mills. Okay, so the example I want to follow for this formulation is the Ward-Chiral model. So let's take the Ward-Chiral model. So this is an equation for a group-valued field G. So it looks almost like the chiral model. So eta mu nu contracted with d mu G inverse d nu G equals 0. So this would be the chiral model. But then this is, there's an extra term which breaks the Lorentz symmetry. So you pick a particular vector V alpha and you contract it with the epsilon tensor. Okay, so this is the Ward equation. So it's some Lorentz breaking, it's a version of the PCM with the Lorentz breaking term. So here, eta is the diagonal metric with signature -1, 1. And V is some space-like vector. So V, so eta mu nu with V mu V nu is equal to 1. Okay. And so this equation can be obtained from a reduction of anti-Self-Geo Yang-Mills. So it can be obtained. Let me very briefly explain how. So anti-Self-Geo Yang-Mills on in the signature that Masashi was using throughout his lecture, the 2-2 signature, because you want to get a Lorentz thing. So you have to, if you remove 1 dimension of time, you're going to be left with -1, 1, 1. Okay. So you start with this signature. So you take anti-Self-Geo Yang-Mills in 2, 2 dimensions. So epsilon ABC d contracted with FCD is equal to minus FAB. So now you do a reduction where you say nothing depends on the third coordinate x3. So you say you want independence of the x3 coordinates. So this is a reduction. And then in that case, you find that the third component of the connection transforms as by the adjoint action because there's no D3 G inverse. Nothing depends on x3. So in that case, you call the third component of the connection, you call it a scalar field phi, which transforms in the adjoint. And what this equation becomes is the Bogomolny equation. So d mu of phi is equal to 1/2 epsilon mu alpha beta f alpha beta. Okay. So this is the starting point in 3 dimensions. Now, if you move to a certain gauge, so where this epsilon mu alpha beta is just epsilon 3 mu alpha beta from this one. You put a 3 in the first slot. So now the point is moving to a particular gauge. So you choose a gauge. Where, the gauge is A0 is equal to A2 is given in terms of some group element G. And then A1 is equal to phi, which is A3, is given by in terms of the same group element. Okay, so this is the gauge, and in that gauge, you recover exactly the Ward-Carroll model with V is 0, 1, 0. So this gives you the Ward-Carroll model. With V alpha is equal to 0, 1, 0. So it's a space-like vector, but you can get by similar reduction, similar gauge, you can get the more general Ward-Carroll equation. Okay. Just to say that here it doesn't look like there's a spectral parameter, but the point is that the anti-self-Yang-Mills equations, as we've already seen, does have a formulation in terms of a flat connection, which depends on a spectral parameter. But the spectral parameter is part of the differentials as well. So it's not really like a flat connection as I've used up till now. It's a more subtle version of a flat connection, which is associated to holomorphic principal bundle on twistor space. And the whole point of the anti-self-Yang-Mills framework is that you can construct exact solutions using the ADHM construction. So although the construction of integrals of motion in this language is not immediately clear, the point is you have exact solvability through the ADHM construction. Okay, so it's in that sense that things that come from anti-self-Yang-Mills are integrable because we can solve exactly the anti-self-Yang-Mills equations, and so any reduction of those equations are also exactly solvable. Okay, but what I'm more interested in is finding if there's a lax formulation that would involve an auxiliary spectral parameter, and that allows you to naturally construct integrals of motion by some similar mechanism to what we had in 1 and 2 dimensions. So given if we have a lax formulation, like the one of the two I had before, the next question is, so given a lax formulation, so choose your favorite from the above. The question is, in 3D, which 5D, so using the same kind of principles we've used all this time, is there a 5D holomorphic topological gauge theory, that produces this. So which 5D gauge theory will produce this? Okay. So as I said, in the pseudo-differential operator form, there's no apparent spectral parameter, so it's not clear that we can go up to 5-dimensional theory to produce that framework. But in this setting where the anti-Saltier Yang-Mills or its reduction to Bogomolny has a lax-dependent, a spectral parameter-dependent lax formulation, there is a 5D formulation, which was originally obtained by Costello in 60 and then reduced down to 5D by Bittelston and Skinner. So let me just say that for the anti-Saltier Yang-Mills, sorry, for the Bogomolny equation, F star is equal to dA phi. You can use this thing which Masahito talked about, this 5D partially holomorphic which I'll abbreviate as PH, Chern-Simons theory on mini twistor space. So the action, which was written down by Bittelston and Skinner in 2020, is the 5D partially holomorphic Chern-Simons depends on a connection A. Let me call it A prime to distinguish it from an A I'll introduce later. So you integrate over a mini twistor correspondence, which is called Pn. So what Pn is just mini twistor space cross R. So this is called a mini twistor correspondence. So this space, and it's given by, it's isomorphic to mini twistor space cross R. So a mini twistor space is a two-dimensional complex manifold, which is itself given by the total space of the O2 bundle over CP1 with fiber some isomorphic to C. Okay, so this is mini twistor space. It's this total space of the bundle of O2, which is a two-dimensional complex manifold. Okay, so then you pick a 2-0 form on MT. So 2-0 form. So yeah, let's call it like this. Wedge, and then the Chern-Simons 3 form for A prime. But because we have holomorphic direction MT and a topological direction R, the differential is just D along the topological direction, the de Rham differential, plus the del bar of the mini twistor space. So it's a standard Chern-Simons 3 form, but with differential that's along the R direction and it's anti-holomorphic along the MT direction. So of A prime plus a third A commutator with A. So the reason it's called partially holomorphic is because it's not quite holomorphic. It's not just del bar, there's also dr. So the partially holomorphic refers to the fact that there's this term here. Whereas the 6-dimensional version is fully holomorphic because the Chern-Simons 3 form is del bar in 3 dimensions. Okay. So I won't say much more about this action, but this is very well, it's been well developed now by Bittelston Skinner, and there's a more refined version with non-commutative deformations introduced very recently by Bittelston Skinner and 2 other collaborators, Hoevelin, and I forgot the fourth one. So I won't talk much about this. I'll come back to it briefly at the end. What I want to focus on is going back to first principles. Let's suppose we have a three-dimensional theory, and we want it to be integrable in the sense that it has an infinite number of integrals of motion. The question is, how do we expect to extract these integrals of motion from some lax formalism? So in 2 + 1 dimensions, so we expect integrals of motions to be given by some surface integrals, by a surface integral over some Cauchy surface. So we have a three-dimensional volume. Let's take R3. And we pick, so time is upwards. We pick a surface of constant time. So some Cauchy surface CT. And just as in the two-dimensional case where we had either a cylinder or the plane, we took a constant time line, constant time surface, and we could integrate a lax connection over that one-dimensional line. A lax connection is one form. Here we expect that integrals of motion might be given by some area-ordered integral of some two connection. So some area-ordered exponential, and this is for the moment very vague. I'm not telling you how to define this, but there is a notion of surface-ordered integral of some two connection. So let me put this in quotes. So for some two-form field B of Z, which depends on a spectral parameter, right? So this is like a two monodromy. Like the monodromy was the one-dimensional, in the case, the object to look at in 2 dimensions to generate integrals of motion. It was the integral of the lax connection over a surface of constant time or line of constant time. Here I'm doing the same thing in 1 dimension higher. Okay, so the idea is to consider not a gauge theory, which has a one-form connection, but a two-gauge theory or higher gauge theory, which has a one-form and two-form connection. So if this is our goal, to produce integrals of motion in this way, the idea for producing a gauge theory that derives or that constructs such a lax formalism would be such a gauge theory should be based on, or it should be a higher gauge theory. So we consider a higher gauge theory. Higher gauge theory version of 4D Chern-Simons for what's called a two connection. That would live on a 5-dimensional space, which is this R3. So that the two connection has, first of all, two components, A and B, where A is a one form, and B is a two form. So I'll explain exactly how this works in a second. But this is the intuition. We want such a form because this has a two components that could be integrated along surfaces. And then it should live on the total space, which will be R3 cross CP1, or in general, some Riemann surface. So let me say, in general, on M cross CP1, where M is some 3 manifold. Okay. So that's the motivation. So I need to tell you about higher gauge theory and to be able to write down this action. So the whole construction will be very analogous to the 4D story I talked about yesterday. And I will skip many steps because it looks very similar. But the difficult thing is understanding the setting of higher gauge theory and what are these objects, how do gauge transformations look like, and so on. So I want to spend a bit of time talking about this. So I'll talk about, the goal is to introduce this 5D. It's called two Chern-Simons because it's built from a two connection. So introduce 5D two Chern-Simons theory. Okay. And to do that, I need to tell you about higher gauge theory. So the basis of gauge theory is to work with Lie groups and connections valued in the Lie algebra. So the objects that we start from here are called, technical term is a strict Lie2 group. So the notion of Lie2 group is the important notion in higher gauge theory or in two gauge theory. So it's two groups. There are two groups G and H, and then two maps T and alpha. So it consisting of, so G and H are two groups. We need a Lie group morphism. T, which goes from H to G. And alpha is an action of G on H. So we need an action alpha. So it takes an element of G and an element of H and gives back an element of H. So, and this action should be in terms of automorphisms. So what that means is alpha of G H H prime. So if it acts in terms of automorphism, it means that an element of the group G, so little g, it acts on H by automorphism, so it acts on a product by the product of the automorphism. So alpha of GH, alpha of GH prime. This is what it means to act by automorphisms. And also two extra conditions, which is that the map T, it intertwines the adjoint action and the action alpha. So that means that T of alpha of GH should be G of T of H, G inverse. So T acting on the action of G on H is the same thing as first acting with T and then doing the adjoint action. So it intertwines the action of alpha and the adjoint action. And also there's this other condition that alpha of T of H on H prime. So T of H is an element of the group G. It can therefore act on H prime with the action alpha. And then this should be the same thing as H prime, H inverse. The adjoint action of H on H prime. Okay. So this is for every G in the group G and H prime in the group H. Okay. So that will be what replaces the notion of group in this higher categorical setting or higher gauge theory setting. So in particular, our gauge transformations will be valued in this two group. The lax connection or the gauge connection will be valued in the corresponding Lie algebra. So let me say a few words about what that looks like. You just take the differential at the identity of this object to get the Lie algebra, or the tangent space at the identity. So the associated Lie2 group or Lie2 algebra is G, H, then T star alpha star. It's the notation. It consists of two Lie algebras. G and H. A Lie algebra automorphism. Morphism. So T star is nothing but the differential of T at the identity. So, and it goes from the Lie algebra H to the Lie algebra G. And then the alpha map, it's more subtle or more interesting. It produces various things. So it produces an action alpha star of the Lie algebra G on H. With all the axioms coming from these things up there. So it acts in terms of derivations. So what that means is alpha star of X, something in the Lie group in Lie algebra G, it acts on a commutator of things in H as a derivation. So this is equal to the action on the first element plus the action on the second element. So that's what it means to act in terms of derivations, such that, so if you differentiate the other two properties, you get T star alpha, T star of alpha star of XY is just X with T star of Y. And alpha star of T star of Y is equal to Y with X, or Y with Y prime. So this is for every X in the algebra G and Y prime in H. Okay. And I said that this action alpha gives rise to more things, because you get a map like this, but you also get we also have two maps, which I won't define explicitly, but if you take differentials in a different way, you can produce a map which I also call alpha star, confusingly. So it's an action of the group G on the Lie algebra H, and also another map, which is an action of the Lie algebra. It's not really an action. Takes a Lie algebra element in G, a group element in H, and produces a Lie algebra element in H. Okay, so these are different ways of differentiating the map. So this one comes from differentiating. So if you take alpha from G to automorphisms of H, its derivative at the identity is alpha star. This is the map from G to derivations of H, which is the one I've been writing here. But then there are two other ways of taking the derivative, where you differentiate in the G slot. Let me not go into the details. There's two other ways of defining these maps. I'll be needing them in a second. But their definition is not so important. Okay. So let me give you an example of this kind of structure. Yep.
I'm going to give an example of two Lie groups.
I'm just going to give you one now.
Okay. It's very good.
Yeah, it's a bit of an abstract object, so let me give you a concrete example, which is the one I'll use at the end for an example of a field theory you can build from phi d2 Chern-Simons. So this example is the main example. Which is called the shifted cotangent bundle, or shifted tangent bundle. So it's denoted T shifted by 1 along the fiber G. And so it consists of a group G, which is the base of this tangent bundle. And Lie algebra is the fiber, but it's shifted by 1, so it lives in degree -1. I'll give you explicitly. I'll explain this in more detail in the case of the Lie algebra. So this is really an abelian Lie group. So you take the Lie algebra G, and you just take the sum as the group operation. So it's the vector space of the Lie algebra, but you take the sum as the group operation. So it's an abelian Lie group. Okay. So what is the map T? The map T is just the identity. So the map T, it should go from the Lie algebra to the group. There's not many maps that do this. And the one that works, which satisfies all these properties, is just to take the trivial map. So it sends any element to the identity of the group. It's very trivial. Okay. So this is T. And then alpha, we need an action of G on the Lie algebra. This is the adjoint action. Okay. And G is just some semi-simple Lie group. Okay, so this, and let me just write, this is the adjoint action. So adjoint action from G cross little g to little g. Okay, so this satisfies all the axioms if you use this definition. Okay, and the corresponding Lie algebra, corresponding Lie to algebra, is, so it's a Lie algebra G with a non-trivial Lie bracket, G sub ab, which means an abelian version where you just forget about the Lie bracket. So what's the Lie algebra of this? It's just the vector space V with no Lie bracket. So this just means the vector space V with 0 bracket, abelian Lie algebra. T is the 0 map. So T star is really the map from which sends everything to 0. And then you have the adjoint action of the Lie algebra on itself. Okay. So what did I mean by the Lie algebra or the group? The group H is in degree -1. At the level of Lie algebras, this is really describing a chain complex. This will be important in a second. So there is really a map from G ab to G, which is T star. And this you should think of as a chain complex. So it's a differential where G sits in degree 0 and the Lie algebra H sits in degree -1. And T star is the differential, which is actually trivial. It's the 0 map that goes from H to G. Okay. Right, so in this sense that the group H sits in degree -1, or the Lie algebra in degree -1, and the Lie algebra G is in degree 0. Okay.
Oh, I'm sorry, what's the gridded structure on the shifted tangent bundle?
On here?
Yeah.
So this is more subtle to define. The Lie algebra is a vector space, so you can talk about a chain complex. Here it's a more complicated structure. Yeah, I don't want to go into that now. I can tell you maybe about it if I remember afterwards. But that's why I emphasize mostly the Lie algebra. At the level of the Lie algebra, it's easy to describe the graded structure because we have a graded vector space And the map T provides a differential which promotes this to a chain complex. Okay, here it's some higher categorical. So these provide morphisms between elements in G. It's the maps between objects are in degree -1. Like this, these are morphisms. This is objects. It's like a category. Yeah. Okay. So that's the main example. But let me go back to general setting now and tell you what a two connection is, which we'll just call connection from now on. And what's a gauge transformation and so on. Okay, so a two connection, or just connection for short, on X, which is some three manifold cross CP1, is a pair. So it's got two elements, A and B. So the first one is a one form on X valued in G. So that's the usual notion of connection. It's a Lie algebra valued one form. But now we have also a two form. So B is a two form on X, but it's valued in H. Okay, so because G is in degree 0, a one form in G is a grade 1 object. And a two form valued in H is actually a degree 1 object as well, because H is secretly in degree -1. So a two form valued in H is actually a degree 1 object. So this whole thing has degree 1. It's a one form in the graded sense. Okay, the Lie algebra carries some grading because it's really a complex. It's like a one form valued in this complex. The part which is valued in here is a one form, an actual one form. The part valued in here is going to be a two form, if you count total degree. So that's a connection. It's a pair of things. That's why it has the right kind of structure I was talking about before. There's an A form, A1 form, and B2 form. Okay, what is its curvature? Again, it's two curvature, but we just call it curvature. Well, let's call it curve of AB. So there's the natural thing you expect, which is the curvature. So this is going to have to be a two form on X valued in G with another part. But the first part, which is the two form valued in G, well, first you can take the curvature of A. That's clearly a two form valued in G. But you can also take the form B, the two form B, and you can act with T on it, because this is a H valued two form, but T star B is a G valued two form. So this is then correctly a G valued two form, right? B is an H valued two form, but if you act with it, if you act on it with T star, H goes to G. So you get a G valued two form. So this thing is called the fake curvature. So it's called the fake curvature. And then there's another component which will have to be a three form valued in H. Because again, H is degree -1, so you can take a three form valued in H that will have total degree 2. So it's a component of a curvature. And you can form that by taking D of B. That's H valued 3 form. Or you can take alpha star of AB. So A is a one form, B is a two form, so this is a three form, and it involves the action of the Lie algebra G on the Lie algebra H, which produces something in the Lie algebra H. So that's in here. Okay, so that's called the curvature. It has these two components. Okay. So yeah.
The possible point is called fake.
Okay. Yeah, this I'm not sure. I forgot. I think because this is the curvature that people are usually interested in when they study.
standard curvature.
It's H, yeah, H, the three-form curvature.
Yeah, three-form curvature. Yeah.
Exactly. This one is sort of, it's not really the curvature, so people call it fake, I think. I mean, I don't exactly know. I can't remember the terminology, but this is what you usually call the curvature, and this is the fake curvature. You're still puzzled why it's called fake. It's just a name. I don't think it's important.
Can you associate a concept of parallel transport to that such kind of definition of curvature?
Yeah. Yeah. I think if this curvature is, if this fake curvature is 0, then parallel transport doesn't depend on the path.
Yeah.
That's true. Yeah.
It's true.
Yeah.
In that sense, it's a curvature.
Yes, but the curvature has two components, and this one, I call it fake curvature because this will be important in a second. It has a name, and that's called the fake curvature. It's just one of the two components of the curvature. That's correct. Yeah.
Okay, thank you.
Yeah. Okay, so now what's a gauge transformation? So a gauge transformation should take a connection to another connection. So a gauge transformation it should be something like this, which takes AB to A prime B prime. And it will have to have two components. So it is a pair. So G and gamma. So G is the usual thing. G is a function from X to the group G. Okay. But then there's another component which it's not a function, but it's a one form. So if you look at up there, the connection, it's a Lie algebra valued one form, G valued one form, and a H valued two form. The curvature is you go up in degree, so G valued two form and H valued three form. The gauge transformations, you go down in degree. So if you take a Lie algebra valued one form, down in degree, it's a Lie algebra valued zero form, or more generally, a global version is the group valued function. Okay. And then if you go take a Lie algebra valued two form, H, the corresponding gauge transformation parameter will be a Lie algebra valued one form, valued in H. So that's the two components of the gauge transformation. So this pair, it transforming the pair AB to, so I'm giving you now a formula for A prime B prime. So A prime is GA G inverse minus DG G inverse minus T star G, T star gamma. So you can check everything is in the right space. So this is the usual gauge transformation of A, the first two terms. And the last term, you're taking a one form valued in H, but you're applying T star to it. So it becomes a one form valued in G, which is correct. It's in the right space. And then B prime is, so you can have alpha star of G on B. So G, the group element G acts on B, which is H valued, and then minus the curvature of gamma. So first, this is a two form valued in H, which is correct. This is also a two form valued in H. So the curvature of a one form is a two form. So it's a two form valued in H minus alpha star. And this is a very weird term, A prime gamma. So this is taking, it depends on the image of the A prime. So A prime is an H valued one form, G valued one form. And so this is the pairing between Lie algebra G and Lie algebra H. So it's the action of the Lie algebra on the Lie algebra. And so this is a two form because A is a one form, gamma is a one form, so it's a two form valued in H. Okay, so that's the notion of gauge transformation. Okay. And then the composition is the standard one. So, there's a notion of composition. These things compose nicely. The composition is, it's very easy to work out. You just do this twice and you look at what the result is. So if you start with AB, you apply G gamma, you get to some A prime B prime as written, and then you apply another gamma G prime gamma prime, and you get to a new A double prime B double prime. And it turns out you can do this whole thing in one go using G prime. So G prime G, that's the usual composition of gauge transformations for one forms. And then gamma prime plus alpha star of G prime gamma. So this is how these things compose. So if you compose two of them, you get back another one, but with these parameters. Okay. So composition works nicely. Okay. So now is where it gets very complicated or tricky, is that there is also a notion of two gauge transformation. Because so gauge transformations are group valued functions in G or Lie algebra valued one forms, but there's clearly, you can transform that using an H valued function, that you can let an H valued function act on the one form. So there's a notion of two gauge transformation which sends a gauge transformation to another gauge transformation. So this is the notion of a two gauge transformation. There is a notion of two gauge transformation. What it does is the following. You have a gauge transformation from A to AB to A prime B prime. Let's call it G gamma. But then you can have a transformation that sends this gauge transformation to another gauge transformation, G prime gamma prime. So it's a gauge transformation between gauge transformations. This is called a two gauge transformation. So this is parameterized by a single element A. And so this is an element A, which is a function valued in H. Okay. And what this does is it transforming the gauge transformation parameters G gamma to G prime gamma prime, given by the following formulae. G prime is T of A G. So A is valued in group H, and so T of A is valued in the group G, and you can left multiply G by it. So this is just how the G part of the transformation acts. And then on gamma, it acts like a gauge transformation. On gamma, gamma is a one form, so you can gauge transform it by A. And then there's a weird term, alpha star of A prime A. So this is the very weird thing where A prime is Lie algebra valued in the Lie algebra G, and this is valued in the group H. So it's the alpha star which takes Lie algebra of G and group H into Lie algebra of H. There were these three maps. So this alpha star is the one that takes alpha star here is the one that takes Lie algebra G cross group H into Lie algebra H. So this produces a Lie algebra valued one form in H. Okay. So that's just the formula that people came to many years ago. But there is a problem with this, and this is a very important subtle problem. So let me say it here. So there's a subtle issue, which is one reason why what I'm going to say is not fully understood and fully developed. So subtle issue is that, of course, if you think about this diagram, for consistency, the gauge transformation of AB by the top arrow should be the same as the gauge transformation of AB by the bottom arrow. So in other words, if I gauge transform AB, well, that's A prime B prime. And that's for consistency. We need that they're equal. If you transform AB by G prime gamma prime, it should be the same thing, of course, because both gauge transformations have the same target. So these should be the same. And the unfortunate thing is that these formulas do not guarantee do not guarantee this. So this holds if the fake curvature, this is why I gave it a name, it's called the fake curvature. So if the fake curvature vanishes, then this is indeed true. This formula does provide a transformation from this gauge transformation to this gauge transformation. In the sense that if you work out this side, so the left-hand side is given by the top formula. The right-hand side is given by the same formula, but where instead of G and gamma, I put G prime gamma prime up there. And if you compare both sides, where G prime gamma prime are given by this, you'll see that they agree only if the fake curvature is 0. So, but otherwise not. So if the fake curvature is not 0, then this formula doesn't work. There must be some modification of the formula that would give rise to a gauge transformation between gauge transformations. So this is known as the fake curvature problem. So in other words, two gauge transformations are only defined between fake flat connections. So two gauge transformations as it stands are only defined between gauge transformations that connect fake flat curvatures. Well, let me just say they're only defined for fake flat connections. And this is a problem for us because we will write an action, and if the curvature is fake flat, the action will be quite degenerate because the fake flatness will be one of the equations of motion. If you impose it from the beginning, the action is becomes quite degenerate. Okay, so this is an important issue to keep in mind. So what we did was just ignored two gauge transformations and just worked with gauge transformations. So in other words, we're not working with the full higher gauge theory setting because it's not fully developed yet to allow for the existence of two gauge transformations, which should be there, but they're not really defined as it currently stands. So basically from now on, I ignore these two gauge transformations, but it'll be important to keep in mind that they should be there because some of the problems that we'll see should be resolved when you correctly address this issue. So now let me write down the action. I can write down the action for 5D two-chern Simons. So I fix a G invariant pairing So between G and H. So such that some, so G invariant just means that the adjoint action of G on the group G on the first slot is the same as the alpha star action on the second slot. Such that T star of Y with Y prime should be the same thing as T star of Y prime with Y. Okay. So to define the Chern-Simons type action, I need a Chern-Simons 3 form, or whatever the analog is for a 2 connection. So I'm going to define this and then explain why it's like this. So define the Chern-Simons. So it's called the 2 Chern-Simons, and it's a 4 form. So it's a Chern-Simons type form that depends on A and B. And the formula doesn't look like a Chern-Simons form, but I'll explain why it is. So it's the curvature of A minus a half T star of B paired with B minus a half D of AB. Okay. So it's a 4 form because curvature of A is a 2 form, B is a 2 form, so this is a wedge product of 2 forms with 2 forms, and then this is a 3 form differentiated. So it's a 4 form. So why is it a Chern-Simons 2 form? Why is it to do with Chern-Simons? Because it's literally the Chern-Simons form for a connection valued in a Lie-2 algebra. So let me explain why this is. So really what A and B are 2 components of a field complex. We have a field complex, which is the following. So this is really a DG Lie algebra. So there's in degree 0, 0 forms valued in H. And then you have, so with 0 forms valued in H, I have a differential DL, which is the sum of the Durham plus T star up to some signs. So I can act with T star on this to get a 0 form valued in G. But I can also act with Durham to get a 1 form valued in H. Okay. And then if I can keep going, I can act with Durham to get so let me write it. So DL, I can hit this to get a 2 form valued in H by Durham, or I can hit this lower thing with T star to get a 1 form valued in G. And I keep going until in top degree I get a 5 form in this case valued in G and then 0. Okay, and then the point is that this is the stuff which is in degree 1, and this is A and B. They are the 2 elements in this degree here. So let me call the pair curly A. Okay, so I have a field complex, and the things in degree 1 are the fields A and B, the G valued 1 form and the H valued 2 form. The things in degree 0 are the gauge transformations. They are the infinitesimal gauge transformations. They're the Lie G-valued 0 forms and the H-valued 1 forms. This is like the G and gamma, or it's the infinitesimal G and gamma. And here is the 2 gauge transformations. So I have the A, or infinitesimal A, which was a H-valued function, or here H-valued 0 form. Okay, so This is the kind of complex you write when you do BV analysis of this kind of theory. So you have the fields, the gauge transformations, which are ghosts for ghosts, and then on the other side, anti-fields. Okay. So now in this framework, I claim that this is a de Lie algebra. So this has a differential. It's a chain complex. So with the Lie bracket of degree 0, so it takes two elements in L and produces an element in L. So this is a degree 0. So the differential has degree 1, the Lie bracket has degree 0, and there's a degree 1 pairing on this thing. So because I had a pairing between G and H, I can use that to build a pairing which takes two things in L and gives me back a de Rham form of degree one more than what I put in. So the degree increases by 1. So if I put in a 1 form and a 2 form, I get out a 4 form. So that's what it means to be degree 1 pairing. The pairing increases the total degree by 1. So in other words, this angle bracket L, it carries a degree 1. Okay, and now with all this notation, I can show you why this action or this Chern-Simons form I wrote above is really a Chern-Simons form, because I can write it as follows. So then, in fact, this thing above, Chern-Simons of A, B, it's nothing but the following. So remember, curly A is the combination of these two fields in the middle. So curly A with DL curly A plus a third. In fact, it's a half and 1/3 factorial, just normalized by a half. And then A with a Lie bracket in L and pairing in L. Okay, so this is just the standard Chern-Simons form, but it's for this one form that really has a 2-form component as well. So this whole thing, because the degree of the pairing increases by 1, this whole thing has degree 4. It's a 4 form. So A has degree 1. It's this thing in the middle. Everything has degree 1 here. And D increases the degree by 1. So A paired with DA should have degree 3. But then the pairing L is also of degree 1. So it increases degree by 1. So that's why this is a 4 form. Okay. And it's really a Chern-Simons form. So it's called the Chern-Simons, 2 Chern-Simons 4 form. Okay. So now I can write the action. Now that we have a 4 form, and we want to integrate over a 5 manifold, we're just missing a 1 form. So just as in the 4D Chern-Simons story, we just fix a meromorphic 1 form. And we can use the same kind of formula as before. Omega is sum over some poles of some levels Li over Z minus Zi, dz. Okay. So it's a 1 form on CP1. And then I can write down the Chern-Simons 5D action. So then consider the action. So S5D 2 Chern-Simons. So it's a different action to the one I wrote before, which was 5D partially holomorphic Chern-Simons. This now depends on 2 fields A and B. And with some normalization, the action is just an integral over my 3 manifold cross CP1. And then omega 1 form, wedge Chern-Simons 4 form. Okay. So it's a 5 form which I integrate over the 5 manifold. Okay, now the story just runs very similarly to yesterday. I had a 4D Chern-Simons, which was built from Chern-Simons A3 form wedge with omega. Now I just have to deal with the fact that I have a Chern-Simons 4 form, which depends on A and B, and I'm wedging it with omega. So essentially everything I said yesterday carries over. So I'm going to be very brief. It's a bit more involved because you have to deal with 2 connections, but it's really the same thing morally. So let me say first, there's same kind of subtleties. The action has potential problems at the singularities of omega. So omega is singular along, now it's some volume defects. So it's the whole space M cross with the poles of omega. But because these are simple poles, but that means the action is actually well defined. But action well defined for simple poles. And then also, because you have zeros in omega, you can allow, and you should allow, A and B to have poles at the zeros of omega. So if omega has zeros, so this is the set of zeros like yesterday of omega, then you should allow A and B to have singularities there. You should allow A and B to be singular along the three-dimensional volumes localized at the zeros of omega. Okay. This is what will produce meromorphic lax connections, which have singular poles, which have poles at the zeros of omega. So in other words, you can define a space of fields. Okay, so maybe from here I'll be briefer. So you can define a space of fields. Which is pairs AB. So one form on M cross CP1 without the zeros, valued in G, and a 2 form valued in M cross CP1 without the zeros, valued in H, such that so every component of A and B which has a Z bar, so AZ bar, but also BZ bar I for any I equals 1 to 3. These should be smooth, should have smooth extensions. Omega wedge A should have a smooth extension, omega wedge B, and then omega wedge the whole curvature of AB. So this is reminiscent of the kind of conditions I imposed before, that certain things should extend smoothly. So these should all extend smoothly to the whole manifold. They were defined initially only on the manifold with the M cross zeta removed, but they should extend to the whole manifold. So this just prescribes how strong the singularities should be at the zeros. Right? The singularities of A should not be stronger than the zeros of omega. Singularities of B should also not be stronger than the zeros of omega. these guys should be smooth. They should have no singularities. And the curvature should have no stronger singularities than A and B themselves. Okay. Exactly as in the 4D case, this action is not gauge invariant. So you can apply a gauge transformation. So you can try and perform gauge transformations and ask if the action is gauge invariant. So if you schematically compute the gauge transformation of, so you take a G and a gamma, and you gauge transform the pair AB, and you evaluate the action on this gauge transformed connection. You find the same action you started with, but there's an extra term which localizes at the poles of omega. So let me just write schematically. So some integral localized at M cross Z bar, the poles of omega. So these are where the omega has poles, and that's where the defects lie. And then the gauge transformation fails, it breaks at those poles. And what I said yesterday you should do is you should introduce some new fields that live on the defects, and they should you should modify the action by adding new terms that couple the bulk fields to these edge modes, and such that the whole action is then gauge invariant. So this is the quick summary of yesterday. In this setting, what you need to do is introduce some edge modes living on the surface defects, and you let them transform in such a way that the extended action is gauge invariant. So, okay, so the action is not gauge invariant, but we can make it gauge invariant. So action is not gauge invariant. Resolution is introduce edge modes. So these edge modes, they live on the surface defects. So they will be the fields of the 3D theory. So this is really a pair K and kappa, which consists of a function on the manifold M valued in some defect Lie2 group, and then a one form on the manifold M valued in the defect Lie2 algebra. Okay. So this is really, it looks like a gauge transformation because it's a group valued function and a H valued one form. And the point is that this is really a gauge transformation on the defect. So such that what the purpose of this edge mode is, it transforms the gauge connection. So if you restrict the gauge connection to the defect, so I star A and I star B. So I'm being brief because it's similar to yesterday. So you take your connection, you restrict it to the defect. On the defect, you can gauge transform it by the edge mode, and the result should be in a subgroup, in a defects, sorry, in an isotropic subalgebra. There's some subalgebra G diamond and H diamond, which are isotropic in some sense. I'm not going to specify. So for some isotropic Lie2 algebra. So it's called G diamond and H diamond. Okay. Okay, and then let me, so once you've done that, you really have, you can get a fully gauge invariant action. So by coupling these edge modes to the bulk theory, so we get a gauge invariant action which will be some S that depends on the fields A and B and the edge modes. It's going to be the 5D two-Chern-Simons action for A and B. That's the bulk term, but then you add a coupling term or coupling terms between the bulk fields A and B and the edge modes K and H. Similar to a 4D case. And then this whole action is gauge invariant if you let K and kappa transform appropriately. Okay, so I have 5 minutes. Maybe I'll skip how you get from this to a 3D theory. It's the same procedure as before. What you do is you fix the gauge AZ bar and BZ bar I equal to 0. Now that you have a gauge theory, you can do that. Then you solve the bulk equations. And finally, you solve the boundary condition. That's the middle equation there. So it's the same steps as before. And what you end up with is a three-dimensional theory. And by design, this three-dimensional theory has a lax pair, AB, which depend meromorphically on some parameter Z, such that the equations of motion. So let me just summarize. As in 4D case, we get a 3D theory for the fields K and kappa. These are three-dimensional fields because they live on M, the three-dimensional manifold, whose equations of motion take the lax form so it's d of A of Z plus half A of Z with A of Z minus T star of B of Z. That's equal to 0. And this D is along the manifold M. It's a differential along M. D of BZ plus A of Z, B of Z is equal to 0. Okay. So point is, this is a flat connection in the higher gauge theory sense. And from this flatness, you can write down this monodromy I told you about before. There's a surface ordered integral, essentially of B, which by the flatness of the connection does not depend on the choice of time in the Cauchy times slice. Okay, so let me just conclude. So I don't have time to give an example, but the example we came up with, it produces something that looks very similar to the Ward model, but there's some extra fields which are coming from these one-form fields. So it's sort of like a version of the Ward model with an extra set of fields that complicates the equations. And we don't know yet how to interpret this. The point is these one-form fields, you might expect that we could, if we had these two gauge transformations, we might be able to gauge transform them away. But remember that we don't have these two gauge transformations because we ignored them. They were complicated. We didn't know how to make them close. So that's why we have these extra one-form fields that we don't like. It's possible that by correctly resolving this fake flatness problem, we can get rid of these extra fields and produce exactly the Ward model. So this is all still work in progress. So to conclude, the main open problems are include two gauge transformations, into the picture. So for this, we need to better understand fake flatness. Or find some other means of doing this. Need to better understand fake flatness, or the role of fake flatness. Then there is this important question of what is the relationship to the partially holomorphic 5D Chern-Simons story that I told you about in the beginning. So let me draw a picture of the various theories and what kind of theories you can build in higher dimensions, and you can ask how these might all be related. So I want to sort of draw like a landscape of the possible theories. So so what you have is 4D Chern-Simons, let's say on R2 cross C. This one I talked about. So there are two ways of generalizing this to higher dimensions. You can either complexify, which means you replace a copy of R with a copy of C. So you increase the dimension by complexifying one of the real dimensions. And when you do that to 4D Chern-Simons, you get so this 5D partially holomorphic Chern-Simons on R. So you have only one copy of R now, but two copies of C. So this is a 5-dimensional theory. And then you can complexify again to get a fully holomorphic 6D holomorphic Chern-Simons on C3. Well, technically a twistor space. Okay. But then what I did today was something different. What you can also do, so this was sort of the horizontal direction, is complexify. What I did today was categorify. So this is complexification, where you take, more precisely, a factor of R in your space-time, and you replace that factor by a factor of C. Okay, but then what I did here was take categorification. So another way of increasing the dimension is to categorify in the way I described today, which is you take something on a space, whatever, and you just add a real dimension. I showed you how to do this with 4D Chern-Simons. You can add a dimension by increasing the categorical direction. So you add you make the gauge field valued not in a Lie algebra, but in a Lie2 algebra, which now has a degree -1 component, and that allowed you to go up in dimensions. So this is sort of the two things you can do. And that thing you can write vertically. So this is 1, 1. But that stops here. You can't go to 7 by complexifying. You reach the top. But now what you can do is you can go down to 5D2 Chern-Simons. And this will be on R3 cross C. So I've just added the real direction. Okay. So this is direction 2. You can do this here as well. You could say this gives me 60 partially holomorphic 2 Chern-Simons on R2 cross C squared. So this is 2, and you can do the direction 2 everywhere, just add the real direction. So it goes on. So this is some theory in 7 dimensions, which is 7-dimensional holomorphic 2 Chern-Simons on R cross C cubed, and so on. So the horizontal directions are, in principle, all these complexifications, and the vertical directions, which can go on forever, are these categorifications. Notice that when you reach this stage here, if you take categorification of 60 holomorphic Chern-Simons, you now have a real direction which you can complexify again. So you can do 1 again to get to an 8D theory. So you can play this game forever. And the question is whether it's of any use. So the other thing I wanted to say is that there is also this story I talked about with 3D mixed BF. which is sort of sitting up there. It's on R cross C. And the way this is related to 4D Chern-Simons is by some sort of deformation. It's related by deformation to 3D Chern-Simons on R cross C. But then here, this is so R cubed. So there's a deformation which breaks the complex structure. So you get an R3, and then you can complexify this to get to 4D Chern-Simons. So the diagram sort of also builds in the 3D BF. It's related to this whole story by some deformation to get from BF to Chern-Simons. Okay. So the very interesting question is whether there's a relationship between these 5D theories, between these 6D theories, and so on. So there's sort of various theories in the same dimension. You get 2 theories in 5 dimensions, 3 theories in 6 dimensions, and so on. And the question is whether there's any relationship between them. And this is something I'm very interested to talk about. Yeah, I think I should stop here. I'm out of time.
Okay, thank you very much for very interesting talks. Okay, so is there any questions from the hall first?
Flat connection is corresponding to the pi 1. So how about this fake flat 2 connection is pi 2 or?
I'm not sure. I don't remember. That's a good question. I need to remember. Yeah, there's some higher categorical version of the pi 1 group for Li 2 group, I think. But yeah, I don't know the answer off the top of my head. Yeah.
Thank you very much.
Thanks.
Concerning the last question of two kinds of high-dimensional Chern assembly.
Yeah.
So both give the same 3D integrable system, or
not quite.
Is there any example which is obtained one of them and cannot be obtained another?
Okay,
yes.
This is a good question. So here I told you can obtain a Ward model. You can obtain all models that you know that are obtained by from Bogomolny or monopole equation.
Yeah.
So Ward model is an example. And this is what we tried to reproduce here, but there were extra one-form fields that we couldn't get rid of. And we suspect this is because we didn't correctly account for the 2-gauge transformations, which might be able to get rid of because remember how 2-gauge transformations act on the one-form part of the gauge transformation is as a gauge transformation. So you could hope to gauge away these spurious one-form fields to probably get exactly the same model. Another thing is that, here there's an extra B connection, a 2-form connection. This doesn't have an extra field, it's just a one connection A. So the lax formalisms don't really look the same, but there's possible ways of turning this data into maybe the non-commutative version of 5D Chern-Simons. I don't know. So there's differences between the two. There's different field content. We don't yet know how to produce the same models in both theories, so there's no positive answer to your question.
I see.
But it's still work in progress. So there's
it looks that the Catalan question gives more complicated lax formalism, right?
Yeah. It's more complicated, but it's intuitively more natural, I would say, because it produces naturally integrals of motion as surface integrals of some connection. So another thing is that you know that from 4D Chern-Simons, Masahito told us that you can build lattice models by looking at Wilson lines in 4D Chern-Simons. In this 5D 2 Chern-Simon story, you can look at Wilson surfaces of the A connection. And these Wilson surfaces, if you take 3 of them, they intersect at a point into one edge of a tetrahedron. So the tetrahedron equation naturally lives here. Tetrahedron equation is known to be the analog of the Yang-Baxter for 3-dimensional lattice models. So I don't really know how the tetrahedron equation fits in here, but here there's a very natural candidate for what the tetrahedron equation is. There's a natural R matrix formed from the intersection of 3 Wilson surfaces, and then you can draw a tetrahedron and two tetrahedrons which are mirror images of each other, like the Yang-Baxter equation is 2 triangles mirror images of each other. So it's a natural setting for lots of questions. So for notions that you expect in high-dimensional integrability, like tetrahedron equations and surface integrals, but it's not yet fully developed, and we don't know what is the connection to this other framework of anti-Saussure-Youngmers.
Oh, okay.
Yeah.
Thank you very much.
Is there any other questions or comments?
Starting from the three-dimensional transaminds, can you also do that categorification to get a 4D theory?
Yes.
And does it give rise
yeah.
to the integrable field theory?
No, because in this column, there's no complex direction, so there's no holomorphic parameter.
Mhm.
So
yeah.
this has been done. There's a paper, it was by someone, Roberto Zucchini, I think, and it was from 2 or 3 years ago, and he constructed 4D two transaminds, but it's on a 4 manifold. There's no holomorphic direction, so there's no link to integrability.
Okay, so is there anything interesting about this model?
Yeah, I don't have much to say about it, but it's interesting. I mean, some people have looked into this more than I have, but because there's no holomorphic direction, it's no link to integrability. So this whole column here is just not integrable. But this you can also categorize. This would be a 4D 2BF, and this might be. I think that I know some people who have looked at this. It's not published yet, but there's some notion of lax connection appearing in this categorified 3DBF. It's not yet known how useful it is, but the point is all these gauge theories, when there's one complex direction, one holomorphic direction, you can build lax objects from it. And the point is that's what I tried to explain in my lectures. These gauge theories with one holomorphic direction, they produce lax frameworks, which are good or not. But it's some way of writing equations of motion for a field theory in any dimensions using a lax formalism so some sort of zero curvature for a meromorphic connection in that dimension. Yeah.
Okay, thank you.
Is there any other questions? Okay, how about from online? Is there any questions or comments from online? Please unmute to have a question. No questions? Okay, let's thank the speaker again. Thank you very much.